through all the media we have for this. So you know about CEFIPRA and Indian European fundings that after that you could apply, especially to get students. So there are very, very good students coming from India. So it's the time to recruit and have science and young people going back and forth. So we have Dr. Sanjukta and Professor Saptarishi put together a very good organization team with a lot of tasks, and you've seen them how efficient they are. So if there are any questions or concerns, please come to them and ask. Everyone is aware that it's your first time in India, and everyone is aware. We already know. Even when we organize a workshop with Belgium, they speak French and they are nearby, there are some cultural differences. So the idea and the spirit is that everyone is free and open about what surprises them and what interests them, and that everything goes smoothly. So I just wanted to have a few words about the program. So some of these things there are very conventional. We have tutorials and talks and posters, and some are maybe a bit unconventional and you are not aware of how it works. And the idea is that we put this together, we just build this together, right? So the first one will be the speedrun presentation of the posters. So the idea for all the speakers there, so I hope we have a presentation. You must have sent your slides or send some slides for poster-only presenters, hopefully. And so I don't know about the order. This is the mysterious part. So maybe it's slide roulette. We will have the slides and a random person will present another slides, and this could be fun. So the main idea is to go slowly for everyone and to say, you know, I'm this person from this group. I had this kind of trajectory before, maybe working in this Indian institute. So everything is new for everyone. So please be slow and take the time to show your face and put some scientific keywords around so that it's easy to go and talk to each other. And so the idea of this speedrun presentation was to get some exposure. We have another session tomorrow afternoon. If you look at the program, it's written follow-up on posters. It's in case we don't have the time to go through everyone this morning. Or also in case, so you've seen or you've read in the emails that also talk presenters, even senior professors, are kindly requested, it's not mandatory, but it would be nice that they print even just a slide of their presentation and they put it up so that, for one, we forget a bit about hierarchy. You know, you will get all the respect you want from the students and they know how experienced you are. But the idea there is that even if someone was outside organizing something and missed your talk, or maybe was worried about getting some medicine for someone who lost their luggage or other adventures, they still have a chance to ask, you know, can you comment about this emblematic paradigmatic curve? So there's no dumb questions. We have jet lag, we have many things to attend to. So don't be worried about appearing dumb, asking a dumb question. I will specialize into that, being the goldfish of the conference and saying, okay, let's assume I didn't listen to your talk or I didn't understand it. Can we go back through it? So please forget about this. So this follow-up poster presentation will be for the speakers maybe to say, I just selected one slide from my talk and come to us. Or maybe to say, I have a dedicated posters from a student that didn't come, and that is a Zoom on this specific thing. Don't be afraid to repeat and to reformulate, to link to what other speakers said. And it's even hard, I know, for everyone to pronounce correctly. I know I'm fluent, I can say Saptarishi and Sanjukta very fast, but I know it's very hard for you. So just check on the program, try to say the name. It's okay, it takes time to talk together. So and the very unusual sessions are there in pink. You've seen that we have two show and tell. So on Thursday at the end of the day, 30 minutes, and on Saturday. And so the idea is that we get to chat to each other about whatever questions you think is interesting, what surprised you, What are the interesting results you've seen in the literature recently? What are the things you don't believe? Like people from the cold atoms might say, I don't think is something actually nice going to come out of warm vapors? And people from warm vapors could say, why are you guys going cold? It's useless. It's all that we are not going to write on the program, but we can discuss between us. So also the idea is what is said in this room remains in this room. I don't mean scientific secret, I just mean I have this doubt. I actually never understood what an atom is. It's okay. Well, for me it's okay. I hope it's okay for you. So this is all I wanted to say. I hope everyone is game for it. And if you are not, it's also okay. We'll see. So I'll let the other organizer if they have something to say.
I think we can go, in fact, for the slides to introduce a bit I would say you, but globally where you are from. Maybe to explain a bit to Indian people how it is in France in Région, in Paris area, how we are organized, because you will see it's very complicated. The idea is not at all that you know how it is. I mean, there will be no test afterwards about oh, it can be interesting, by the way. You see, but at least to understand some keywords, to understand who is where, the locations. You will see there are many universities. Okay, I will try to explain it just a bit to give you a flavor of how French administration can be. You can compare it to the Indian one.
So we are going to present some slides which will tell you about the origin of how this workshop was started, the planning and everything. So where's the funding coming from? And then I'll also tell you about the history of Raman Research Institute, where this workshop is taking place. So we can go to the slides.
You have my slides?
Yes,
so
yes.
You can use your computer only. Okay, so thank you. So first, I would like to thank all our sponsors. So in fact, there is a specific agreement between the Région Île-de-France and Karnataka, mainly about education, and that they wanted to strengthen a bit research, and they contacted Paris-Saclay University, International Relationships, who contacted me because they knew I used to have collaborations with India. And this is why we are all here now, so thank you to Région Île-de-France. And then there are some funding also coming from many university Paris-Saclay through different, I would say, sub-institutes inside. Institute for the Sciences of Light, Quantum, and all this is part of France 2030, which means how to improve innovation and in the next years. So thanks also for Raman Research Institute to welcome us. So you can see here Karnataka and Île-de-France regions on the map, because I don't know if you have an idea of where we are. And if I go to Île-de-France, you can see how many universities we have. A lot. So, okay, in this you do not have science for all of them, but it's really difficult. There are some regroupments with different Paris-Saclay University is a regroupment of other universities. It's very, very complicated to understand. You have Institut Polytechnique de Paris, which is not a university, which is, I mean, you know, in India, IITs, IISCs, universities. Okay, it's more or less the same in France. IITs engineering schools, you have IISCs are more or less école normale, and you have universities. So it's the same for us, but some of our universities, like in University Paris-Saclay, can merge both a university, in 3 times, university like IIT and IESC, because we have university parts, we have engineering schools, and ENS. So you might see sometimes one name, a kind of ENS, École Normale Supérieure, like an IESC. We have one in Paris-Saclay, there is one inside Paris. Sometimes you will see these logos. You have also the Collège de France, which is a very old institution, you see 1530. And you have, so it's hard to know exactly where you are. So if you happen to come to Paris, be careful, you can be completely lost if you did not pay attention to where you are going exactly. If I go more, so people in this audience, the French part, are coming from these specific institutions. And if I go on a map, you can see not everyone is at the same place. There are only some people inside Paris. Inner Paris really is the center here in the more, the darkest part. Then Paris-Saclay, you can see, is here, close to Institut Polytechnique, but they are really separated institutions. So you have people here from Sorbonne Paris Nord, one lab, Laboratoire de Physique des Lasers. And here even in Paris-Saclay, you have again another institution which is kind of a national research agency, ONERA. Thank you, thank you very much. So, but please talk to people, and if you want to see and to visit us in France, you're welcome, but be careful where you are located, because it's not very close. Just to give you a flavor of the thematics, you can see Nadia spoke about hot and cold atoms. You have people from cold atoms, hot, warm vapors, at room temperatures. You have light in complex media with atoms. And so, yes, again, talk with people. And if I put the names of everybody here, you will forget this immediately, so I didn't do it. And I think I let now Sanjukta present a bit the Indian part.
Hello. So here you can see the photograph of Professor C.V. Raman, who's received the Nobel Prize in 1930, and you'll be happy to know that this is the same auditorium and the same table where he was giving his lecture. Yes. So I'll just tell you about the lots of research institutes we have in India, who are working in under the National Quantum Mission, which was launched in 2024, and RRI is the lead institution for quantum computing with neutral atoms and ions, and many of the member PIs and the lead PI is here in the audience. So I'll go to the history of RRI. So this, I'm happy to organize this workshop along with Nadia and Fabienne. And we had planned this workshop, from 1 year before, and so this is the result of all the discussions and hard work we did all this time. So let me come to the history of Raman Research Institute. So the Nobel, Professor C.V. Raman, he had received the Nobel Prize in 1930 for his work on the scattering of light and for the discovery of the Raman effect, which was named after him. So in December 1934, the government of Mysore, which was the kingdom at that time, at the time there were the India was divided into many, many kingdoms. There were kings and nawabs, and they were so they had a lot of land. So the government of Mysore, they gifted a plot of land to in Bangalore to Professor C.V. Raman for creating Raman Research Institute as a reward for his Nobel Prize in 1930. And in the same year, the Indian Academy of Sciences was founded by Professor C.V. Raman. It's right here at the corner. You can have a look while you're having a walk around Raman Research Institute. So C.V. Raman, he founded the Raman Research Institute to continue his studies in basic research after he retired from the Indian Institute of Science. And he served as its director, carrying his personal research until 1970, when he passed away. And it was funded completely personally by him with donations from private sources. So here you can see some photographs of Sir C.V. Raman in Raman Research Institute. And here you can see, here it's the same corridor where you have put your poster. So here you can see Professor C.V. Raman here. And here is his collections in the Raman Museum. So today we have organized a tour for you in the Raman Museum, where you can see a lot of fascinating collections by Sir C.V. Raman, including precious gems, musical instruments, stones, and whatnot. I'm sure you will be amazed by the collection. Now Raman Research Institute is an autonomous research institute which is funded by Department of Science and Technology, and it's engaged mostly research in basic sciences and now also in quantum technology. And Sir C.V. Raman was a true visionary, and he said that the true wealth of the nation does not consist in the stored up gold, which India had lots of them in those times and also now, but in the intellectual and physical strength of its people. So we follow his footsteps and his vision, and I'm sure you will enjoy your stay and this workshop at Raman Research Institute. Just to mention, I have a strong French connection because I did my postdoc in the lab of Nobel laureate Claude Cohen-Tanauji and Michel Leduc in LKB at École Normale Supérieure, and also at Institut d'Optique with Philippe Grangier and also Alexei, who is present here in the workshop. So now I invite Fabienne for the next part of the session.
Thank you. I don't know if so we have the pleasure to have with us some representatives of the French consulate. I don't know if you want to say a word or...
Hi, hello everyone. So I'm Antoine Guillemet. I'm the attaché for academic and scientific cooperation at the French consulate in Bangalore. We are very happy to have you here today, especially for the French people who I understood a lot of you are new to India. It's the first time to come to India. So the French consulate is active in many domains, but especially in the field of academic and scientific cooperation. And as it was said, we have a special partnership between the state of Karnataka, where you are here today, and the Paris region that we try to strengthen. So the activity here today at the Raman Research Institute, together with the Indian Institute of Science, IISc, is a very good example of that. The idea for us is to strengthen academic collaboration It does exist in India, between France and India for a long, long time. We mentioned the CIFIPRA project, but the idea, as you may have heard, from the government's perspective, is to encourage to have more student and academic mobilities between France and India to France as well. So in both sides, it's one of the big motto of our president, Mr. Macron, to strengthen those mobilities. And a lot of them happen within the framework of what we call a memorandum of understanding, so an agreement between two universities. So I see that a lot of French and Paris universities are represented here today. If we can use this as a platform to strengthen the existing collaboration and be able in the future to send and receive more students and have more professors coming to teach in France or coming here to teach in India, that would be good. So yeah, I'm very happy to see this activity here today. And once again, yeah, very warm welcome to all of you. Thank you.
So maybe we can now begin the speedrun session. So I don't know, it's on this computer that you have who has the slides for the organizers?
Alan, okay, he's not there.
Oops. Yes, check. And we will ask all the people who gave their slides maybe to come here, because we don't know also which one is, we don't know the order, so be ready to, to speak. Magnifique. De toute façon, ils verront. J'ai demandé de venir.
Okay. So we are in the order of the poster. So it should be number 1, Elizabeth. Number 2, Adwait. Order. Elizabeth, you're first. Is it okay? We can. Okay. So Elizabeth, Adwait, David, Kevin, Juan, Nadia, Saga, Goku, Romain. No slides tomorrow. Okay, so Romain tomorrow, Rupak, and Hippolyte. Yeah, this is what I just said. Okay, so I don't know, 11 people, no, 10 people in 30 minutes, so it's actually very easy. You have 3 minutes. Relax.
My name is Elizabeth Gliot. My name is Elizabeth Gliot, and I'm currently a postdoc at Lumine Laboratory at École Normale Supérieure. And so I did my PhD at the Laboratoire Kessler-Boissel in Jussieu. So what I'm working on right now in my postdoc is superradiance and subradiance in an assembly of quantum dots, and more particularly to model theoretically what happens when we have pure dephasing in our system, which usually occurs when we have interaction with phonons, for example, which tend to destroy superradiance and subradiance. And so the idea is to find thresholds for the dephasing rate. And this is a project that I'm working on with Sébastien Kistrebert, Jean-Sébastien Loret, and Nikos Fayard, who is right here in the room. So the main idea is when you have emitters that are close to each other at sub-wavelength distances, then you have collective effects. So you have collective emission that changes the decay rates, and you have a dipole-dipole interaction, which causes an energy shift. And the idea is that if you want to include dephasing, then you have to take into account the dipole-dipole interaction. So either you can model this with a local approach, where the dephasing acts independently on each emitter, but this has problems because then you violate certain thermodynamic laws. And so another approach is to use what we call the global approach, where you express the dissipation with global operators from the collective eigenstates of the system. And so then you have an extra temperature dependence that comes into play which is basically the ratio of the energy of the interaction and the temperature of the system. So if you want to learn more, then you can come and see my poster. Thank you.
Which one is the laser pointer? Laser pointer? Sorry, laser pointer? Okay. Advait. Good morning, everyone. I am Advait KB. Actually, I did my PhD here at Raman Research Institute from 2015 to 2022 at LAM Group with Professor Andal Narayanan. After my PhD, I did my two-year postdoc at Wigner Research Center for Physics at Hungary. And from 2023 October onwards, I am working at Lumin with Professor Fabia Pratenecker and Fabian Goldfab, who is here. So I am mainly working on the Rydberg atom sensor project. And Rydberg atom is a highly excited atom where it has very high dipole moment. With this feature, we can sense very weak electromagnetic field. So here you can see that we achieved the Rydberg atom state on the rubidium-85 atom on a vapor cell by introducing two different lasers. One is an infrared laser, and there is a coupling laser which is a blue laser. And with this kind of setup at certain conditions, we can achieve something called an electromagnetically induced transparency, where if you expect an absorption of the probe field, with this setup, with the electromagnetically induced transparency setup, one can achieve a transparency window there. Okay. Now, if you apply RF field with around 17 gigahertz in our case, it can be microwave or RF field, or So if you apply that, you can split these levels. So this is coming from the Artleton splitting, and with this splitting, you can actually measure the RF field, electric field strength. Now, this is the conventional setup of an RF receiver, but it's really good sensor, but it has one disadvantage, which is the bandwidth. So now what we do in our lab is to modulate the coupling field with a phase modulation, and with that such a setup, due to the nonlinear interaction, we get a intensity modulated probe output. So we can call it as a modulation transfer protocol. The modulation is transferred from the blue laser to the infrared laser. Now, with such a system, we can achieve a high sensitivity. Also, we can connect two different Rydberg states, Rydberg levels, so with two different RF frequencies, okay? And we can have a continuous, nearly continuous RF sensor compared to a conventional protocol setup where we have very bad sensitivity in between, so you can't connect it. So this method introduces, give us a better continuous broadband sensor. And the poster, I'll talk to you more about the poster outside. Okay, thanks.
Yes, hello everybody. My name is David Teidl. So first of all, I want to say that I'm very excited to be here in India. It's been a pleasure so far, and thank you to the organizers. I'm looking very much forward to it. So I did my PhD at Laboratoire d'Optique Appliquée, which is part of Institut Polytechnique de Paris, which you have seen in the introduction before. So with my PI Hamid Majdi, we were investigating the strong field effect of high harmonic generation. Right now I'm a postdoc with Alexei Yumtsev, who will give the tutorial today at Collège de France, but my poster will be entirely about my PhD work, because I'm still a very recent postdoc. So my PhD work is investigating non-classical effects on high harmonic generation, and just very shortly, so high harmonic generation is a frequency up conversion process and a strong field regime. So usually we send infrared pulses into some interaction media. And then there inside there's a very nonlinear process happening, and you get out like a broad spectrum that ranges from the visible to the XUV spectral range. So this process is usually described within a semi-classical three-step model. And in my PhD work, we were looking into a more recent development which aims to merge quantum optics and these strong field processes. And especially the question that I was looking into was, are there intrinsic non-classical properties in the state emitted in this high harmonic generation process? So to investigate this, okay, it's the second point. So we were looking at photon correlation measurements from high harmonic generation generated in various semiconductors. So we estimate photon statistics and evaluate different non-classicality criteria. And with this, as I can show you in my poster, we showed the first experimental evidence of non-classicality inside this process of HHE in semiconductors. So in the bottom you have some scheme, general scheme of what is happening. So if the pulse is coming, then we have some interaction media. In our case, this is the atoms arranged in a crystal, and then the emitted light, which we are investigating. Yeah, thank you.
Thank you. Okay, so I already did just one slide, sorry, and there's not my name on it, so I think I missed the point. Anyway, thank you for having me. So I'm Kevin Falk. I just defended my PhD like exactly 1 year ago. And I did it in LKB, in the Fluids of Light team, under the supervision of Alberto Bramati. And now I'm still at LKB as a postdoc, but in another team, another group, with Quentin Glorieux. And I'm doing more like atomic physics in warm vapors of rubidium atoms. So less collective effect in some. So I decided to do my poster on my PhD work, but we can, of course, speak about what I'm doing now. Okay, so I worked with a kind of, not exactly cold of warm atoms, but the system, we can speak about it later. My work was about, let's say you are interested in a black hole, okay? And especially the mechanism that can allow him to lose energy. In 1970, Stephen Hawking predicted the Hawking radiation, which is a quantum mechanism that enables a black hole to lose energy. This mechanism is triggered by quantum fluctuation, and if you are located at the event horizon of a black hole, which is the non-return point for light, you have, triggered by quantum fluctuation, the emission from vacuum of a positive energy particle propagating in the outer space and a negative energy one inside the black hole. These two particles are entangled, and you see that I injected negative energy in the black hole and escaped positive energy, so it loses energy in some sense and a mass. So it's a crucial prediction from a thermodynamical point of view. So for sure it's something that you want to tackle experimentally, which is not possible on real black holes. Why? Because the Hawking radiation in terms of temperature is too cold with respect to the cosmological microwave background, so you can't see it. So some people in the tens of years later tried to find some system in which you have basically the same equations without the problem of the real black hole, and it turned out that you can do it with fluids. And I can explain you in a very simple manner how. Imagine a river that is flowing from left to right, and if you are in the upstream region here, you have some fish inside. They have a constant velocity, let's say in blue here, and here they go faster than the fluid, so they can move freely, basically here. Here the fluid is too fast, so they're dragged by the flow, and they eventually fall in the waterfall. So you have here a kind of point of no return for fish, and in some sense you created a fish black hole. But of course I'm not interested in fish in my experiment, and not in a classical fluid. I'll use a quantum fluid, which is microcavity semiconducting polaritons. You can also do it with atoms. And the things I'm interested in, of course, are not fish in my fluid, but are collective excitation, so Bogoliubov excitation in the fluid. So yes, my poster will be about how did I created an optical analog black hole, if you want. We can also discuss about, am I really simulating gravitational effect? It's another debate, but of course. Yes, that's it. Yes, don't hesitate to come and see my poster. Thank you.
So, good morning, everybody. It's really a pleasure to be here. Thank you very much for the organizers. I had never been this far from where I was born. It's pretty much the other end of the world. So my name is Juan Rafael Alvarez. I am an assistant professor in Télécom Paris, which is one of the institutes composing the Institut Polytechnique de Paris. Fabien already mentioned these are engineering schools, a little bit, you know, this is a French specificity of engineering schools, which are not exactly like universities, but students go to get the training, and after they're done with the engineering school, they can continue with a research career, with something like a PhD. Two more things, just in case you want to ask me, these are things that I can also mention. The first one is that this year I am an ambassador for Optica, for the Professional Society of Optica. So yes, these are lifetime, but the cohort is the 2026 cohort. So if you have a student chapter, if you're interested, ask me questions. I'm happy to help. And the other thing is that I also coordinate an international laboratory with the University of Laval, which is in Quebec, with a collaborator that used to be a part of Télécom Paris. So what am I going to be talking about? I am going to be talking about how to use warm atomic vapor for quantum networking, right? So we have seen that atoms are actually this very nice platform that can study a lot of different phenomena. And one of the ideas that we want to tackle, because again, we're a school focused on telecommunications, on networking, is this idea of really being able to emit entangled photon pairs, in particular here in polarization, using warm atomic vapor. So this is an idea that has been actually tried by many groups in the past. But one key contribution, something that has been interesting about the warm atomic vapor, is that you don't tackle it exactly under resonance, but you go very far detuned in such a way that you can address all the velocity classes of the atom to make a source that is actually bright and usable, albeit limited by the Doppler effects in the vapor. So if you want to know about this, and another thing that I should mention is rubidium actually has a lot of nice transitions. So for example, one of them for emitting photon pairs. The photon pairs that you can produce with this sort of medium are going to be one around the atomic transitions of rubidium, meaning that you can interface with something like a quantum memory, and another one that is going to be a telecom wavelength, and therefore great for quantum networking purposes. So the other two things that I'm going to mention, so for now, even though we're building the source, again, I became a professor about 1.5 years ago, so be patient with the results that we have. So far, we've only had one student once a week working for 6 months on a saturated absorption spectroscopy setup. But the idea would be really to develop and deploy this sort of source. And the other nice thing that we have is an infrastructure for networking in the Paris region. So we have many different institutes from which we have members here in the auditorium that are going to be talking about different applications. But we have many different institutes connected by optical fibers, and therefore we can test many of these protocols for quantum networking purposes, and especially for quantum networking purposes, that coexist with the current classical communications. And then another thing, you also find a little poster to acknowledge and to promote the activities and the research opportunities that we have in the Institut Polytechnique de Paris. In particular, what is called the PhD track, which is a little bit like an Americanized system where you applied for a master's, and you start with a 2-year master's with the possibility of continuing with a PhD. So that's it for me. Thank you very much.
So, hello, you've seen me already, but now I have a different hat. So I'm Nadia Belabas. I'm a CNRS researcher. Officially, so is there a pointer? Ah, yeah. Yeah, so it's a laser. As you can see, I'm an experimentalist. Okay. So I'm working at C2N, which is somewhere. So, learning is about reinforcement. France, Paris region, zoom on Paris, and something like 20 kilometers to the south, accessible by train. Fabienne said it's far, but there is a train. You can get with wonderful RERB to the Paris-Saclay region. French people are laughing about RERB. You will ask about the private joke. And soon a subway, actually, yeah, line 18. You will know all the details from the Indian people. You're going to be fluent in Paris paraphernalia. And so somewhere close to Institut Polytechnique, you will find the newly founded C2N with a clean room here. So we can fabricate nanostructures. They're silicon resonators. And this is really across the street from Telecom, where Juan is working and then is an assistant professor. And we are connected by the fiber. Here it's Telecom Paris, and here it's C2N. So only 650 meters. But then you can go up to Paris, Lipsis, and LKB, where a lot of people, so LKB people, can you raise your hands, please? And Collège de France, soon to be LKB. Yeah, we're there. So we have LKB people. MPQ is also inside Paris. So this is all the network. So I was expecting, there is some rainbow in here and rainbow in there. So I just wanted to say, I was a student at École Polytechnique that you heard. I did my PhD at LOA that was mentioned by David, soon to become LOB, in femtosecond sources. I did a lot of Fourier transform. I worked with parametric sources of non-classical light, both in the discrete variable and continuous variable regime. I worked with artificial atoms, quantum dots. I'm now working with silicon resonator in quantum communication, quantum computation, and soon quantum sensing with Priyanka, who's at the back of the room. So I'm into rainbowness and diversity, bringing several people together and several flavor and things together. So I haven't worked yet with true atoms. I'm going from the top-down approach, going lower and lower, and I'm very much interested in collective things, true collective effects, or collective people doing collective thing together. So for science, what I decided to present here is the work I'm currently doing between Telecom and C2N, together with Juan that you just heard. So you can encode information in discrete variables along logical zeros and one. There are usually polarization in historical setup, and you can play with polarization with birefringent material, half-wave plate, quarter-wave plate, and make a 1-qubit gate this way. People also have recently, and I was really very much part of this effort, encode information in photonic integrated circuit, where you encode information in dual rail encoding. A path would be a 0 and another path would be a 1. And this might not be as scalable as you want, but you can also choose to encode information in colors, in energy. So one example would be to give one frequency qubit to each different frequency of the frequency comb that is from this silicon resonator that was fabricated at C2N in collaboration with ST, which is also in Grenoble in France. So that's one way of encoding, and this gives you access to QDIT, so dimensional, yeah, I'm late, we don't care. So multi-dimensional QDIT, 0, 1, 2, additional robustness to errors, and more fun for theoreticians. So that's, when you have a QDIT, you can certify distributed computing and these kind of things. And it's also almost continuous, because this is what from a mathematical point of view, it's not a quadrature, but it can also be a continuous level of freedom, a degree of freedom. So we can talk about it. And the equivalent of beam splitters for path, birefringent materials for polarization, in our case, is off-the-shelf fiber device, such as electro-optical modulator and programmable filters, so we can discuss this at the poster or anytime. So to have added time, I'm also organizer, to say that Juan didn't mention that his poster on opportunities at PhD will also be mentioned at the specific career session that we have at some point in the program. So this career session will be for everyone to ask questions or promote the kind of programs they have in their institute for exchange of students, as mentioned by people in the consulat. And also now you might be convinced that this kind of exposure, presenting the posters and presenting yourself in person, is different from what you get giving a talk, or different from what you get just standing at a poster. So for speakers giving a talk, you will have your chance to just present a slide, to present yourself also personally in terms of your trajectory, which might be useful for the career session later. So please, speakers, senior people, take the opportunity to give your poster to our nice organizer for the session tomorrow afternoon. Okay? Number 7.
Good morning, everyone. Myself Sagar Sutradhar. I was a PhD student here, and I completed my PhD 2023 under the guidance of Professor Saptarshi Chaudhary. Then I joined European Laboratory for Nonlinear Spectroscopy in Florence as a postdoc from 2023 to 2026. Then I joined back here from February onward. So today I'll be discussing the main theme of the experiments, what we are having here in QMIX laboratory. So basically we are working on 2 main projects. One is the quantum mixture experiment, and another is the flagship experiment, the neutral atom-based quantum computer, which comes under the National Quantum Mission. So here is the experimental setup in our laboratory. So we successfully, in this first project, we successfully implemented the cold atomic mixture experiment here, where we do have 2D plus mod, one for sodium, another for potassium, and here we create the cold. By the way, am I audible? Hello. Yeah. So here we create the cold atomic beam, and we direct the cold atomic beam to the 3D mod, where we simultaneously create cold 3D mod of sodium and potassium. And in the lab, routinely we get more than 1 billion of potassium atom and 500 million of sodium atoms. Okay, so now next idea is to transfer them to the science cell. So now currently we are reducing the temperature of the cold atoms using compress mode and subdoppler cooling to transfer them in a magnetic trap right here. Then using a series of magnetic coil, we would like to transfer to the science cell. And then idea is to transfer them in a cross dipole trap here. For this purpose, we have a 50 watt 1064 nanometer laser, where by opening the trap, we'll be reducing the temperature further, and we'll be increasing the phase space density to achieve that quantum degeneracy. Okay, coming to the next one. Okay. So this is, as I said, that we are developing India's neutral atom-based quantum computer. So this is the the CAD model of our system. So we use the rubidium atom, rubidium 87, and we use the F equal to 2 and M F equal to 0 state, and F equal to 1 and M F equal to 0 state as our QB state, and we use for the quantum gate entangling operation, we exploit the Rydberg blockade mechanism, and for this purpose we use the 2-photon transition, so the 420 nanometer and 1013 nanometer. So here the experiment starts from here. So using a cold cloud of rubidium atoms right here, and then we superimpose the static trap onto that, and we create this static trap using 850 nanometer laser beam, which is, and we imprint a phase on that 850 nanometer laser beam using special light modulator, and we send this light through this microscope objective, which creates this dipole pattern. But the loading of the atoms from this atomic cloud to the static trap is stochastic, so that gives defected array. So to generate this, to generate the defect-free array, we use acousto-optic deflector to, and we make this defect-free array, and we use this microscope objective to capture the emitted photons from the single atoms, and we image on the CCD camera. And the entire experiment and the real-time feedback is controlled by this National Instrument PXI system. Okay, so now we do have more projects, and also these are the ongoing projects and outlook. For example, solid and physics in quantum mixture, and in interspecies interaction in induced disorder, mediated interaction, and also as Nadia said, this would be a common point of interest where we would like to scale up the qubits to millions. So for this purpose, the photonic integrated circuit will be important, and this is our teammate. So, okay. And you can find us, and please feel free to talk to us. Thank you very much.
Hi, so my name is Gogul. I did my PhD in RRI with Professor Sadiq. After the PhD, I joined LKB as a postdoc, and currently, very recently, I joined Mirega, which is a spin-off from the same lab. So at LKB, I worked with Roma and Jakob in the group of atom chips. So when you think about Fabry-Perot cavity, generally you have two mirrors which are parallel to each other and forms a cavity. But the idea of fiber Fabry-Perot cavity is the same, but now you have, instead of macroscopic mirrors, you have a mirror which is directly machined on the fiber, and this forms microscopic cavity which has very high finesse. This was developed in our group initially fully for quantum mechanical application, and more recently this has been used across various groups and various fields. So one of the limitation with the fiber cavities is because of the way the fibers are, it limits the inherent mode matching efficiency. So we showed that in applications where like mode matching efficiencies are the most important, you can always go to a plano concave geometry and then achieve a mode matching efficiency where you don't have any secondary modes even up to minus 40 dB. So we will talk about this in the poster. And then the question is, so generally, as I mentioned, this mirrors are directly machined on top of the fiber. What limits the length of the largest cavity that can be formed is the physical dimension of the fiber itself. So there are some applications where you might need not like macroscopic cavity, but something in between where it's few centimeter long, but you need all the advantages of fiber integration. So with the same geometry, we have also built a hybrid cavity where the input is fully fiber integrated and you have a plano-concave single mode fiber, and the output we have a macroscopic mirror which gives us few centimeter long cavity with a like similar finesse. So like in this poster I will mention about all the applications of this platform, how we use them to do a highly tunable optical filter, and how we use also some of this application for self-injection locked lasers, and even like the how we perform cavity enhanced spectroscopy in such a fiber fabric perocavity platform. So if you are interested in any of these topics, feel free to visit the poster for more details.
Hello, I'm audible, right? Okay, first of all, thanks to the organizers for giving me the opportunity to present our work here. And okay, let me introduce myself. I'm Rupak. I'm a PhD student in the theoretical physics group here at RRI. I'm writing my thesis with Professor Dibyendu Roy. He'll give a talk tomorrow. And I mainly work in quantum optics problem, on waveguide QED related problems, and quantum transport, and little bit on spin noise spectroscopy theory in collaboration with Professor Saptarshi Choudhury. So, but the poster that I'm putting outside is based on the work which came out last year. It's a part of my thesis, and it's basically on quantum transport problem in atomic chains. So let me give you very plain insight in this problem. So it's a boundary-driven problem in which a mesoscopic system is coupled with two different reservoirs such that you can maintain different chemical potentials on this reservoir to drive a current through it. But this is not an ordinary system. You can engineer the system such that it can simulate a balanced gain and loss dynamics. That is to say, it is possible the particle can be injected and taken out from the middle part of this chain, but in a balanced manner. And we got interested in this problem following a vast literature on PD symmetric systems. These are basically non-Hermitian formalism to deal with such gain and loss dynamics. And in this literature, it exists that to get the rectification, that's to say non-reciprocal transport in such system, one really needs to go to nonlinear wave propagation regimes. So we did not formulate our theory using PT symmetric formalism, rather than we tackle this problem from a more statistical point of view. So what we did is basically fix the average rate of injection and extraction of particle in this medium, and then use master equation description for the classical regime, as well as quantum Langevin equation description for the quantum mesoscopic regime. But keeping these technicalities aside, the results what we got is quite interesting. What we got is that we can get rectification behavior now in the linear response regime in the systems. And to understand that, we try to figure out what is the role of inelastic scattering to the onset of this rectification behavior. We also got some results on quantum to classical crossover, as well as how quantum interference effects in such system will give non-reciprocal to reciprocal phase transitions. Okay, so that's it. And if you're interested in all these blue highlighted buzzwords, then please come to see my poster. And you can catch me anytime you like, and I will be happy to explain this all in details. Thanks.
Hello everyone, my name is Hippolyte Mouana. I'm a postdoc in the SIA group in LPL in Sorbonne Paris Nord, in the north of Paris. I did my PhD in the same group on molecules confining spectroscopy of molecule confined thin cells. And now I'm working to develop an experiment of selective reflection with mether material and sense the near fields with atomic vapors. So for my poster, I'll present you the quantum near field sensing with atom and molecular gases. So in our team, we study the confined gases, like confined gases. There is two ways to study spectroscopically this. So there is this selective reflection here, where we probe the atom, which are at a distance of lower than lambda over 2 pi, where lambda is the wavelength of the transition. And the thin cell spectroscopy, where the gas is confined in a thin cell, which is a cell where the thickness is nanometric, micrometric, or nanometric. So we can study the Casimir-Polder interaction, which is vacuum due to vacuum fluctuation, and in near field we can consider that it's the dipole, like the particle, it's a oscillating dipole, and it induces an image on the surface, and this induces electric field and make the Casimir-Polder interaction. And so we can see that there is like a shift due to this interaction. And thanks to this experiment, we can also probe the parasitic electrostatic field due to charges on the surface, for example. Oh, there is no title here, but this technique, it's high resolution spectroscopy, so we can also use it as to know some spectroscopic parameters. And for example, here it's a molecular spectra of SF6, and we obtain some lines, and it's interesting because it's a molecular interest for atmospheric studies physics. So if you want to talk of everything, my poster is just here. Thank you for your attention.
Hey, hi. So there is a request. Who have not sent their flash talk presentation, kindly do share it. And okay. So with your poster number, kindly send it to alan@rrimail.rri.res.in. Thank you.
Yeah, I send it to the WhatsApp group for the people from France. I think this is concluding the first poster session. So I have already poster number 25, Boumidja, number 16, Elwin, number 19, Nargis, number 18, apologies for the wrong presentation. You'll set me right by presenting your poster. Number 18, Parajmit, and number 20, Shrutis. I hope it's all right. So I'm saying again, for speakers, anything is a poster. So just put your badge on the poster, print anything, and come up in front of the audience to just say, hello, it's me, and I'm friendly and approachable, and that will be nice, okay? So we can also use the follow-up poster session tomorrow afternoon for a second chance. For people, for poster 1 to 12, who felt it would have been nice to show a picture of themselves and people in their group, or want to do it again, I think we will have time. So please drop by these wonderful ladies or send an email to Alan at blah, 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 to say, okay, I'm using the second chance. Everybody is a goldfish here. We will have forgotten you, so you can get more exposure and say the things you forgot to say because we were jet lag on the second row. Okay? If none of the other organizers have something to say now, I think it's time for lunch, so we shall go at the terrace where we had breakfast, you will notice that the spot for lunch is written lunch for imposters. We are not quantum enough to be in two places at the same times. So the idea is you have your food, and when you're done, or whenever in the discussion it arises, you come back here and discuss around here. This is India. There will always be chai and coffee, and you can bring your food around, and everything will be smooth. I think it's time now to thank all the speakers of the sessions, including the nice indication we had from Consula about exchange and scientific mobility. So a big round of applause. And another one for the wonderful organizers, because you just noticed the speed run presentation is very useful at the beginning, but it's kind of acrobatic to organize. And the music wasn't her phone ringing because she's not organized. It was to say your time is up. So you should know everything is done quietly but wonderfully well by the organizers. So thank you very much for this. Okay, food and discussion. Ah, oui.
Okay, I think we can get started slowly. So, my name is Athanasios Laliotis. I am an associate professor at the Université Sorbonne Paris Nord in the north of Paris, if you remember the little map that Fabienne showed. I work in the Laboratoire de Physique des Lasers, the LPL, and I have a talk about my work on Thursday morning, and I'm here with Hippolyte Moina, who's right over there, who used to be my PhD student, and now he finished his thesis. And we both have posters outside, so you can come and look. And I will be the president of the chair of the first session here. So I will ask the speakers to kind of introduce themselves a little bit in the beginning, as we all have. And I'll keep the time. So the first speaker for today will be Alexei Urjumchev, see if I'm pronouncing it well, who is from Collège de France. And he will talk about nonlinear quantum optics. It's an overview and a preview because he also has a second talk. So Alexei, please.
Hi. Thanks for the introductions. Thank you everyone for being here. Thanks for the organizers for inviting us. It's been a great time so far. So I'm Alexei Urjumtsev. I work in Paris, just downtown. What you don't see behind my back is a Notre Dame church, like 200 meters away. I'm a quantum optics person. I did my PhD on parametric quantum optics and on Gaussian light generation, then a postdoc on cavity QED in Germany. And then I've been doing stuff that I'm going to present mostly during my second lecture tomorrow. And so today I'm going to be talking about something that all my different projects since the beginning of my PhD had in common, and this is nonlinear quantum optics. Now, what does that mean? Let's start. I mean, this is supposed to be a workshop about quantum technologies. So one of the basics that people learn in quantum technologies are DiVincenzo's criteria for what's a good qubit. It's a system that you can physically isolate. You need to initialize it in a specific state. You need to be able to make single and multi-qubit gates. You need to store your information, detect it efficiently, and ideally, you'd also like to transmit it over a long distance. You can do that with tons of different things. If you try doing these with photons, some things are easy, like transmission. That's basically the only qubit for which it is easy. And some things are hard. There's 3 of them, and I'm going to be talking about 2. I'm going to leave aside the storage. This is the story about quantum memories, which is going to be for another day by somebody else, maybe. I'm going to be talking about 2 major issues that these things have, is that it's not that easy to isolate a physical qubit. It's not that easy to make single photons. It's not the hardest, but it's not that easy. It's also not that easy to make multi-qubit gates. And to do both, this and that, you need to engineer interactions between photons at the individual level. Here is kind of a nonlinear absorption where you send tons of photons in a system and then only one photon comes out. Here is more like nonlinear dispersion where one photon is going to change the phase of another by something like pi, and then you can turn that into a control NOT gate with linear optics and so on and so forth. So this is what I'm going to be talking about, is different ways that people know so far in the field for doing these kind of things. What's in common between this and that? What's the difference also? And so let's go. The first one is projective measurements. That's called cheating. Because here photons don't actually interact. It's kind of an effectively induced interaction by measurements. The idea that you could make an entangled state, measure part of that to do something on whatever's left is very old. It's basically the EPR paradox. And the times where people started seeing that was during the Bell experiments by Clauser and Aspey in the 70s and 80s, where you had a photonic cascade in an atomic warm gas. And then when you detected one photon in one state, the other one was in a symmetric polarization state. It didn't take the same group of people up to permutation very long to figure out that they could use that to make a single photon source. They just took the same experiment, they detected one photon, and then they sent the other on a 50-50 beam splitter, and they saw that indeed there was only single photons coming out. Now, you can call that a single photon source if you want, but frankly speaking, it's a source of not more than single photons. What came out of that machine was indeed not many photons, but most of the time that was nothing. It was extremely inefficient. About the same time, Hong and Mendel, whom you know from Hong-Wu and Mendel effect, figured out that you could do exactly the same thing in a way easier fashion by using parametric optics instead of atomic vapors and vacuum chambers and ion pumps and all this circuitry. You just shine a blue laser in here, and sometimes a blue photon breaks in a pair of red ones, and if you detect one here, you know, there's one there. So that's easy in principle, but it took people another 15 years to figure out where and when exactly that photon was, because the model structure of what's emitted from this guy is not as trivial as this picture suggests. And then they could actually take photons that were, or at least emit photons that contained more of a single photon than of vacuum, to the point where they could interfere that with a classical laser beam and make a homodyne tomography and see things like negative linear functions. And from that point on, you could claim that you could engineer a pulse where you knew where there was mostly one photon. It's an active field that's developed from those times. There's an experimental review that's on the archive, a theoretical review by one of my colleagues, if you're interested. Of course, you're going to have these slides, so you don't have to write these down. Now, problem. When you see exercise on my slides, it's a calculation that I was to laser. I just didn't have the time to make explicitly, but this is really something that you can do yourself if you want to convince yourself that this is true. It's a typical undergrad level quantum mechanics, nothing more. So, as an exercise, you can take that Hamiltonian or evolve, start from a vacuum system, take that Hamiltonian, apply it for a given time, and calculate the output state here, and that output state turns out to look like this. It only contains photons in equal numbers, and photons here and photons there with that coefficient. And then if you calculate the probability of having exactly one photon here and one photon there is going to be at most 25%. So in the best case, that source works one time out of 4. And the rest of the time, you have either too few or too many photons. It's probabilistic. It's bad, but bad doesn't mean it's hopeless. No. When you roll a dice and you want to get a 6, well, you don't always get a 6, but you have to roll it and roll it and roll it. Or you have a bag of dice and you roll all of them at once. That's called multiplexing. You can take a bag of dice and roll all of them at once. This is special multiplexing. You have many of these sources. You shoot a laser pulse in all of them at once. One of them is very likely to click, and then you route that photon to the output. So you need many of these sources in parallel, and then you have to have n layers of active switches to actually route your photon where it should go. This is what quantum tech companies do. Many quantum tech companies building optical quantum computers use that approach. Here, if you do that in free space, it's fairly easy to get low losses and low noise, but everything's very slow. If you do that in integrated optics, these circles here used to be red until recently, but they've been making a lot of progress. So I turned them to orange, and it's probably going to get green very soon. So let's see. If you are an academic lab and not a big company with tons of money, you can do temporal multiplexing. You just have one source, and you repeatedly press the button until it works. And then when it works, you store the outcome in a quantum memory to be used whenever you need it, right? Same story is now fairly easy to get high efficiencies, low noise, high retrieval efficiency, but the storage time is typically not so much bigger than the inverse success rate of that source yet. You can make your life slightly easier by merging these two steps into one. Merging these two steps into one consists in having a read-only quantum memory. The previous one was write and read out. This one is a read-only. You just directly project your quantum memory in a single excited state, and then it spits out a single photon. It's an idea by what's now called the DLCZ paper from 2001, Johan Wilkins-Rakenzoller. And that consists in taking an ensemble of emitters. My emitters are going to be atoms just out of a habit, but it can be something else. Shining a weak laser and waiting for a photon to be scattered on that transition by just detecting that through polarization or frequency or whatever you like. When that happens, you know that one atom transitioned. You don't know which one, and if your detection system is set up correctly, you end up in a state where your excitation is delocalized between this atom excited and that atom excited, et cetera, with phase factors that are going to involve your wave vectors and the positions of the atoms. So this is how you create that simply excited state. Now, if you want to turn that into a photon, it's very easy. You just blast a bright laser, and because this state works effectively as a quantum phased array antenna. A phased array antenna is something that you know from like undergrad electrodynamics. You have one in your pocket in case of that. It's a 5G phone. Then this thing is phase matched to emit in a specific direction, and this photon goes in a well-defined mode. Okay? There again, storage times are not so great so far, but making tons of progress. And this is how people demonstrated for the first time a two-photon gate back in 2003. A two-photon gate is nothing else in that paradigm as a linear interferometer, where you have two photons at the input. The photon A is a qubit encoded in state 0 here, state 1 here, and photon B, state 0 here, state 1 here. You send that through beam splitters, nothing else, and then you post-select, and this is crucial, on one photon being either here or here, and one photon being either here or here. That's just the name of the game. If I had like 5 more minutes, I could actually do the whole math for you. I'm not going to do the whole math. I'm just going to give you the ingredients so you can do that at the coffee break if you want. The only thing you have to know is how a beam splitter works. And the beam splitter takes two modes at the input, turns that to modes at the output, and you can connect them through these equations, which you typically know from your undergrad electrodynamics. Okay? You take that and you apply that to this. You get these equations. Okay, it looks horrible, but that's really all there is. I'm not going through them. This mode is going to turn into that. This one is blah, blah, blah there. You have to post-select, of course, the atoms where there's one capital A and one capital B, as we said. And because there's, through some interference effect, some terms here cancel out, you end up with this, 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 and that. And if you look closely, here, the zeros and ones are swapped with respect to the B mode here. So that exactly does have an effect of a C naught. It works, and until recently, that was the best way of doing things. The problem is that it has a success probability of 1/3 to the square, so that's 1/9. So it's not efficient to do that in parallel. And you need identical photons. Identical photons is something you can have by better engineering. Success probability, you have to be, smarter. So, because ideally you do not want your source or your gate to work in a probabilistic way, people started thinking about how you can do that deterministically. And one idea you could have, if you have some expertise in optics, is to sit down and think like, wait, if my goal is to make a controlled Z gate on my photons, where one photon flips the phase of another, like a light beam shifting the phase of another is nothing else than a Kerr effect, which is something you have like everywhere in optical fibers and so on and so forth. So people started looking at it. And imagining experiments where your photons would be sent in a long and thin nonlinear waveguide with a chi-3 nonlinearity. And so one photon would be imprinting a phase on another, so the output state would look like this. This would be your unitary operator. So if you send one photon same thing. The other photon, same thing, because there's nothing to phase shift it. But when there's two photons coming in, you get a minus sign because of NA being 1 and NB being 1. And so that was the basic idea. There were a few experiments that had been started in the 2000s using typically hollow core fibers with gas in it because it's very confined, it's very long, it's very nonlinear, that has everything. And it took a little while for people to get the idea that it could not work in principle, not just in practice. And that was kind of an interesting point. I'm not going to go through the details of that paper, which is a bit technical, but again, I just give you a hand-waving argument about why this cannot work in principle. And it's simple. It cannot work in principle because to do what I just said, your photons have to be in the same place at the same time, right? Now in physics, same place, same time doesn't mean anything. It has to be finite. To be finite, my photon's duration has to be smaller than my system's response time. This is the only physical time that I have. But now if you Fourier transform it, that means that the photon spectral width is bigger than my system's bandwidth. So some part of my photon spectrum does not get the effect that I want to imprint. And that means that my state that is initially single mode ends up multi-mode, with multiple modes getting different phase shifts. And if you don't manage these modes, I mean, you cannot squash that down to a single mode back again. Sounds like a showstopper, but quoting John Bell, what's proved by impossibility proofs like this is lack of imagination, right? Prove me wrong on that one. Well, to prove wrong somebody, you just have to make the initial hypothesis wrong. What's my initial hypothesis here? I said same place, same time. If my interactions are non-local, the same place goes away. If my system is controlled dynamically, the same time doesn't have any sense, right? The system's response time doesn't have a well-defined meaning. So this is what you can play with. You can dynamically control your system, etc. And now, I'm not going to go more on that. I think Alban is going to be speaking about waveguide KD a little bit. So he's going to be, yeah, like more than a little bit. So I'll leave the rest of that discussion to Alban. And I'll focus on something that's been really the workhorse of deterministic nonlinear quantum optics for the last, I don't know, I'm just making up things, 30 or even 40 years. Single emitters. A single emitter, which as I said I will be calling atom because I'm just so used to it, is the simplest source of pure non-Gaussian states. If you excite an atom, say on a pi transition, and you just wait, you know that it's going to emit a photon that's going to be single, that's going to have a well-defined temporal envelope, which is just going to be an exponential, and that's going to have a well-defined spatial envelope, which is just given by the dipole radiation that you know from, again, from undergrad. The only drawback for using this system as is that this big donut doesn't fit in a lens. Even if you actually physically stick your atom on the surface of a lens, the collection efficiency you can get is, in the best case, about 30%. And you collect something that's really not nice Gaussian nodes, so you lose another 70% of that when you try to couple that into fiber. People have been trying a lot, but still, so far in free space, you do see effects, but it's kind of hard. Now, I'm repeating myself again. Basic quantum physics, what's this shape given by? It's given by the coupling of your atom to the fluctuations of vacuum around it. If you can change the density of electromagnetic states around your atom, you can change the shape of this thing. And this is how and why people started putting cavities around it. So let's take a single atom, two levels with a dipole transition from G and E. It's right like this. It has some energy. Let's put a cavity around, which is described by creation and annihilation operators. It's just a harmonic oscillator. And because the field in the cavity is going to be coupled to the dipole of my atom, I have an extra term, which is my dipole times my field, where I can simplify things a bit if my coupling is smaller than my frequencies, which is the case in optics, which is not always the case in microwaves. So you have to be careful. But in optics it's true, and I'm going to stick to optics. And then you end up with the famous James-Cummings Hamiltonian, which all of you have seen at least once in your life. That thing is what enabled very nice non-Gaussian quantum states with trapped microwave photons, be it in the experiments of Serge Haroche, in an actual bulk cavity, or in circuits. But that's, again, trapped microwave photons. Ideally, what we'd like to is to have traveling optical photons because it's nice to be able to send them around. So to get these things out of a cavity, I need to add something in my equation. I need to make my closed system open. So I need to describe it a bit differently. Let's make things simple. I just assume that everything's in resonance. And then I have to add the fact that my cavity can decay. It can have a useful decay where I actually collect my photons, this is kappa 0. But that photon can also be scattered by a scratch on a mirror, and I have this kappa parallel. And I'm an experimentalist, so unfortunately I cannot forget about kappa perpendicular. Okay? And the atom can also decay. So now I consider that my Hamiltonian is just this because I just put everything on resonance and made a rotating wave approximation. And then I have to add these two decay terms, one for the cavity and one for the atom. And if I want to use that as a gate, sending photons in and out, I have this extra term coupling my input field to the cavity field and the output field to whatever I have. And that's all the ingredients you need, really, to work with that system. For example, another exercise, if you want to do it, you do it. If you want to have the results, send me an email. I'll send you a PDF, okay? Just for fun. You can assume that you start from an excited state, you don't see anything, you don't send anything on the cavity, so this goes away, that goes away. And you sit down, you just solve these equations, and you show that the efficiency with which you can emit a photon from that stuff is given by that relatively simple formula. You can do it yourself, it takes like half an hour maybe. It's the ratio of the useful losses by the total losses times this factor, which is going to be haunting us until the end of this lecture and tomorrow, which is depending on this parameter called the cooperativity. So the name of the game here is that if you have a high cooperativity and if you're dominated by these kappa 0 losses, so this would be called the bad cavity limit because the cavity decays faster than the atom, then your source can be efficient. I see Nadia frowning. Kappa 0 is, on the previous slide, is the useful cavity decay, and kappa, and this is the useful, this is my transmission, this is my scratch on the mirror. Okay?
So people can interrupt.
Yeah, people can interrupt. I don't have to make it till the end of my slides, or I can skip a few things, okay? Question? You. I told you I will be comparing sources and gates. Can we turn that thing into a two-photon gate? From a pic... Single atom.
So what cooperativity we are using, like this what really stands for? Because I see that's like strong coupling limit if you define for cavities, you are writing something like that.
So the cooperativity in that case is the square of the coupling parameter. G is given by the dipole times the vacuum field of a photon.
That formula. I'm asking that formula looks like the strong coupling limit kind of.
It is.
That C greater than 1.
Yeah.
Right?
You need to have C much bigger than 1
Okay, so
to work. Yeah. Absolutely. You have to have C much bigger than 1 for this factor to be close to 1. Absolutely. Yeah. So from what I've drawn here, it looks like you can use that to make a two-photon gate because you'll be sending one photon that's going to be resonant and the second one will not. So typically one photon is going to go through and the second one is going to bounce off or something like that. The answer is no. I'm fooling you, it's not working. And it's not working for the same reason as I told you before for this waveguide Chi3 system. The Shapiro argument, the causality thing, two photons being at the same place at the same time, sorry, okay? You need to add something to that thing to turn that into a gate. You need to add an active control knob. So with atoms, that's reasonably easy. With atoms, all you have to do is you add a third level here and a classical laser, which you can now, as an experimentalist, turn on and off or ramp up, ramp down. This is going to be your active control knob. Now this active control knob appears as an extra term in your Hamiltonian, and nothing else changes. And again, this is a slightly longer exercise. It's a system of 5 equations and not of 3 equations that you have to solve, but I think you can do it. You can again calculate the efficiency of that source now by placing your atom here and assuming that your omega, just for the simplicity of the calculation, is much smaller than the coupling. And you'll see that you get the same result, but without the gamma down in the button. So now what I told you before is no longer true. You don't have to be in this bad cavity limit. You don't have to have kappa much smaller than gamma because gamma goes away. And you actually get that same result in many different limits. This one where kappa is much bigger than G, or that one where omega involves slowly. Now, why do all these different limits give you the same result? That's because if you restrict yourself to a single excitation subspace. I have a single excitation. It can be either a photon and my atom sitting down here, or an atom excited here, or an atom excited here. It's a 3-state system. It's a Hamiltonian that you can just write like that. It's that state coupled to that one with G and that one to that one with omega over 2. You can diagonalize it while I'm speaking, and you get 3 eigenstates, 2 bright, what's called polaritons, bright states, because they're containing a fraction of this E, which fluoresces, which you do not want to happen. And this dark state, which is a superposition of a photon and an atom in this storage state. And if you do things slowly and adiabatically, and this is what all this means, is adiabatic evolution, then all you're going to be doing is rotating your state from being a photon to being an atom in this storage state. So the field that you're going to be emitting is actually going to be controlled by your laser and not by spontaneous emission. Right. Now I told you that now by adding this control knob you could make a gate, and to make a gate, again, you start from the previous equations. You assume that you have a strong cooperativity, which is what you mentioned, that you have a good cavity, no scratches on mirrors, and that the input field involves slowly, so it's again this adiabatic approximation. Adiabatic approximation means that when you calculate these expectation values, you can assume all the derivatives to be 0. And then you'll see that if your atom is in a storage state, it's as if it was not in the cavity. You just have the bare cavity resonance, and your field gets a -1 flip. While when it's in this state G, you get the vacuum Rabi splitting, and your input and output fields are related via this simple formula, which is roughly 1 when C is large. So you get, yeah? Oh, here. Slow time scale is the slow growth and decrease of my input field. Basically, you can assume that A in is constant here. Fast are G, kappa, and gamma in this case. But for practical purposes, you can assume that you're in a steady state to get these results. Okay? And in that case, you see that you have your input field flips phase depending on the state of the atom. And this is the ingredient you need to make conditional gates. It's going to be a conditional phase flip on the field induced by the atom. So this is how Gerhard Rempis and his colleagues made the first deterministic two-photon gate 10 years ago. They had a single atom in a single-ended cavity. They sent qubits encoded in pulses, where the atom could be in either spin down or spin up state, so this is my 0 and 1. And the photons could be circular left or circular right polarized, and only when this atom was in the state up and this photon was circular right, did it get a -1 phase flip? Otherwise, nothing happened because nothing was resonant. So again, not going to go through the math, but I'm going to keep it on my slides and then send you the slides and so you can do it. They started by making a pi/2 pulse on the atom, just to make this superposition, then sending a first pulse on the cavity and getting this -1 flip in that state up there. Then making a -pi/2 pulse. It makes the state slightly simpler, but it keeps it entangled because it's just a local operation. You send the second pulse. Now it gets a bit longish. You make another pi/2 pulse. It gets even longer, but all you have to do at the end is measure whether in state up or state down. And if you are in state up, shift the phase of one of the pulses. And there you end up in a state that's entangled and where this is a plus, this is a plus, this is a plus, but this is a minus, which gives you the effect of a control Z gate, which is the same thing as a control not up to a unitary. Okay? You can just go through the math yourself later on. So the summary of that part is that this approach can be done in many, many different ways in practice. You can actually take a single atom and stick it between two mirrors. You can take a quantum dot and put that in a microcavity. You can try to take an atom and put that next to a microresonator where waves are running in circles. The good thing is that all these setups can be compared through exactly two dimensionless numbers, dimensionless figures of merit. One of them is the extraction efficiency of your photons from the cavity, and this is the ratio between the useful losses and the total losses of the cavity. So that's just the probability for my photon sitting in the cavity to be emitted in the right way and not scattered by a scratch. And that, when you look at that formula, tells you that the transmission of this mirror should not be too small compared to the losses, which are unfortunately always finite. You would like to take them to zero, but it never happens. And unfortunately, that goes against the other constraint of having a high cooperativity, which I rewrite here, and can be rewritten as the inverse of the total losses, so transmission plus losses, times the surface of my atom divided by the surface of my photon. So there, the game is to make your photon as small as possible with respect to the surface of your atom. And the surface of your atom in that case is the scattering cross-section, so it's typical lambda square up to a factor, okay? And so here the challenge is to make very good mirrors without scratches. Here the challenge is to keep your atom steady where it should be and not move left and right, because everything is very, very small, and as soon as it moves by a few tens of or hundreds of nanometers, it gets uncoupled from your standing wave in the cavity typically, or from that evanescent wave.
In your three examples, you have ideas of orders of magnitude of variability?
With atoms in Gauss experiments, it's of the order of 10. And this is where, I mean, people now in optical cavities, wait, what do you have? Huh? 100, okay. So people behind you have 100. Who says more? Okay, okay. That's the typical numbers. And unfortunately, we're just orders of magnitude below circuits. People in circuit QDs, like they start from 10,000 and then up. That's just disgusting. Yeah.
Because you are mostly talking this with cavity, right?
Yeah.
Like the Dayan paper
Yeah.
given, they try to do in the band cavity lineage, and even recent work tries to do these things without cavity, like people call it waveguide QED. Have you heard some?
Hey, tomorrow. Thursday, okay, yes.
So that's possible also in optical regime?
Yes, of course. That's what Alban is doing. Yes, just come back on Thursday. Okay, I have 5 minutes, 7 minutes. 7 minutes, awesome. Last part. Knowing that putting atoms in cavities was somewhat hard, people came up with a fourth approach, on which I will finish, which consists in using atomic ensembles. The game here is that you take an atomic ensemble with tons of atoms in it, so you're going to be certain that it's going to be like optically dense, and your photons are going to hit one of them. You take your photons, you send them in, you convert them into atomic excitations, and you make the atoms talk to each other. This is something that you can do, okay? And then you reverse the process, the photons go away, and they keep the memory of that interaction. That's the story. Some of that story, I told you already. The store in the ensemble and get them out. This is a quantum memory. Told about quantum memories. Quantum memory, in my approach, or with atoms, how many people do it, is you take an atomic ensemble, you couple your photons in that transition, and you have this control laser, again and again you have to have it, that sits on that transition. Your photon arrives, you ram this laser down, and you convert your excitation from here to there, and again, because everything's coherent, it's delocalized over your ensemble with some collective, with a phase vector that depends on the beam geometry. You want to convince yourself that it works? Same story. It's a three-state system, this one, that one, that one. The Hamiltonian is just the same one as you saw before. The eigenstates are exactly the same ones as you saw before. So if you do things smoothly, adiabatically, if you don't shake your system abruptly so that you do not excite these bright states, so the bandwidth of your photon has to be sitting in here, then all you do is you rotate this dark polariton from being a photon to being an atomic delocalized excitation in the storage state and back. This is quantum memory in 30 seconds. I could spend another day on that, okay? Now the ingredient that you have to add is interactions. Ground state atoms do interact, otherwise BEC folks would be out of business. But they interact very slowly. The energies are typically 100 hertz at distances at about 100 nanometers. It's bad for quantum optics. We want things to be stronger and faster. So the idea people had was to take that state from up there and take it up there. Use a Rydberg state. So Rydberg atoms are basically glorified hydrogen atoms which just try to become ions and stopped at the last second. It's an atom where an electron is flying somewhere far, far away from the nucleus, and that has tons of exaggerated properties. For example, the energy, I mean, if you remember your hydrogen atom, it basically scales like for the hydrogen atom where this m is my principal quantum number, slightly corrected for the fact that it's actually not quite a hydrogen atom, but it doesn't make a big difference in practice. So the energy goes as 1 over n square, and where we sit up there for n equal about 100, it's typically 100 gigahertz from ion. So you have to be careful about, black body radiation kind of things. The level splitting, of course, goes as 1 over n cube. The dipole-dipole interactions is just the charge times the distance, and because the energy is inverse distance, you get this n squared here. The lifetime is also quite long, surprisingly, for quantum optical experiments. And of course, the reason why we use them is that they interact like hell. They interact like hell because there's so many states up there so that it's very easy for two atoms excited in the same state to find a pair where one atom goes down and the other one goes up by almost the same amount. And so this makes that process not too off-resonant. Now, if you write this down, the Hamiltonian between this state and that state, it can be written like this. This is my energy defect between this that makes it not quite energy conserving. And this off-diagonal term is my dipole-dipole interactions that square from, again, classical electrodynamics as dipole square over distance cube. If these interactions are smaller than delta, which is the regime that people often use, you just make a second-order expansion, and you see that your state is essentially gets shifted by this amount. And you take all the scalings from down there in here, and you end up with a scaling factor with the principal quantum number to the power 11. So it's super fast. Okay. The effect that this has is called Rydberg blockade. Okay, I'm gonna finish on this, and then I'm probably gonna keep the stuff that I wanted to see here for my tomorrow's lecture. It's probably going to be better that way because it's going to make itself consistent. I'll just finish maybe on this slide to explain you the basics of how things work. So this is Rydberg blockade. I guess many of you have heard of. It happens that if you excite a Rydberg atom somewhere, because of that blockade, you cannot excite another one nearby with the same set of photon and lasers, just because these interactions shift this energy of resonance from my excitation. Okay. This is how people building quantum computers make them work. What that does in quantum optics is that if I send a single photon in my gas, it's going to propagate as the dark polarity that I mentioned before, and then get out and nothing's going to happen. The other case is that if I do the same experiment, but there's already an excitation in the gas, then I cannot turn this thing into a dark polarity because of this Rydberg blockade. And typically, in this case, my photon gets scattered. Or at least I don't have this polarity business anymore. Should I stop now? You know what? I'm going to stop now. And it's up to you. I can give the examples of what people have done. And that's going to take me 2 minutes. Yes. 2 minutes? And then I'll going to be at my conclusion. So what people have done in the past. The first experiments they've done, they use blockade to create single photon sources. You send a weak coherent beam in here, one photon goes through, the others get blockaded and scattered. There's actually two ways of doing these things using the same mechanism. One is using the blockade, which is what I just said. And the other one, which worked historically first because it was easier, is using the dephasing. In the first experiments, the blockade was too weak for this to be true. So what they had was that. They had a small collection of these blockade spheres. They could have several photons entering the gas. But when they were in the gas, because they still interacted while propagating, each of these components acquired a different phase depending on the distance between the excited atoms. Okay? And because of that, these phase-matched phased array antenna broke down, and these photons were scattered all over the place. But all of them, including the first one. So the subtle difference between this guy and that guy is that with this guy, both have a very good G2 below 1, but this guy can be efficient, while this one, if you just calculate whatever you can have from an input coherent state, the efficiency is bounded by 1/E. Okay? Of course, the next step people thought of was to shift this beam off resonance so that the first photon could not only change the absorption, but also the dispersion, not only the imaginary, but also the real part of the optical index seen by the second one, and to make two photon gates. One photon goes through, the second one gets a pi phase shift because of that nonlinear dispersion. That has led to a first kind of proof of principle of a gate, but not super efficient. But there's another body of work where you let several of these photons propagate through a long gas, and because they change the group velocity dispersion around them, they can attract or repel each other, depending on how you tune things, so you can make photon-photon molecules. And if you look at them in the right phase space, you can see things like optical vortices appearing when these things propagate, essentially because when they bunch, they have to depopulate stuff around them, and they get phase flips at some point. You can also get photon subtractors, not deterministic, because fundamentally you cannot subtract photons in a fully deterministic way, but this is as close as it gets to deterministic. You send a bunch of photons in your gas, you literally shake it, make your atoms move so stuff dephases on purpose. A first photon gets stuck in, and the others being detuned propagate through. Sure. So this is going to be my last slide. I'm going to keep the caveats of that approach for tomorrow. There is a lot of work in that field now. There is some historical paper by these co-authors, quite well known, and tons of experimental groups working on that. These are few review papers. I'm going to skip the following slides. I'm going to explain you why they don't work. Sorry, that was a mishap. And take questions from there, okay? So this is my conclusion for today about different things I've presented. I haven't presented the limitations of that approach because it's time for me to stop, and that's going to be a good starting point for tomorrow. Okay?
And then questions, yes?
Yeah, so to clarify, you have a control beam
Yeah.
which is on. That is the G2E in the first excited state that
Yeah.
you, right. So so in experiments that we have been doing,
Uh-huh.
okay, this is experiments in a moat
Yeah.
with lithium, all right. We were trying to climb up the Rydberg ladder,
Yep.
okay, and so we started in a moat, and then we put an excitation from 2p to 3s.
Yeah.
Okay. The moment we did this, we saw a huge amount of molecular ions. Okay. So the question is, the class of Rydberg atom experiments that you are showing, how, I mean, the molecular ions are formed due to autoionization. And in fact, this has been done in collaboration with the French anyway.
Mhm.
So it's an Indo-French collaboration
With
paper.
Aimé Coton, right?
Aimé Coton. And so the question is, what is the occurrence of molecular ion formation in this class of experiments? I mean, and does it really matter to you guys when you are, I mean, is it a constraint on how far you can push these in applications?
So I think ions is the first thing you see when you turn these experiments on. Like if you just have a mote, you shine in your red laser and your blue laser, you see the cloud exploding because of ions. And this is what happens. So of course, that is in principle a limitation. To avoid that, first you should shine short pulses, not continuous. If you shine continuous, it breaks down. For us, it's not a big limitation because we send in pulses that are like microsecond long, and then we reinitialize the system and so on and so forth. What ends up being a problem, though, is what people call Rydberg pollutants. Rydberg pollutants, it's like pollution. I have my atom that I described as a 3-level system, but actually there's tons of levels up there. So because of black body radiation or collisions or whatever you like, sometimes my atom can jump to a nearby Rydberg state, and then it's uncoupled from my lasers and it stays there forever. It is a big problem for many people. For us, the solution is to work with high-lying Rydberg states. They're so high-lying that we can, between each experimental cycle, pulse an electric field that's generated by electrodes, which is just low voltage electrodes, about 10 volts. And then it ionizes this thing, and the ion flies away. And then we still, instead of having 1,000 atoms, we have 999, which doesn't make a big difference. Yeah.
Can I do a follow-up?
It's up to the next speaker, not me.
So we have a coffee and tea break, actually.
Yeah, we are going to the next talk and we move the coffee break.
Oh, I don't know. I heard there was a crisis, but I thought it was resolved. And actually there is tea. That's what I heard, yes. I was checking. So, well, there is a tea break. There was a crisis, but it was resolved. And so we can follow up the discussions.
Yeah.
So maybe there will be one question from someone young.
Yes, indeed.
No offense meant, but
Yeah, guys, I'm here all week. I have a poster which is just right here, number 13. It's more about what I'm going to be talking tomorrow, but just go ahead. Yes.
And you compensated with another factor of 2 in your topic.
Yeah, so there was a factor of 2 in my definition of cooperativity, and I have this factor of 2 following me all over the place. It's really a convention. People have different conventions for cooperativity. I think we had a workshop with people doing cavities about a year ago when we agreed that we should all sit down and agree about the definition of cooperativity once and for all. Jacob was there, Romain was there in Jacob, so I don't know what was the favorite. But I think that one people kind of like the most, but I don't even have a strong argument why. You cut down this factor of 2? Yeah. Okay, it's just a convention.
So you just want the...
For the Rabi frequency, so for the Rabi frequency, you have the theorist convention. Exactly. So in my equations, you always see omega over 2, and that just comes, the 1/2 comes from a cosine average. And the theorists find that ugly, and they take it out, but then they give you numbers on your Rabi frequency that you have to generate, and you end up with 4 times too little laser power because they forgot that too.
So just a small parenthesis, this is a typical topic for the show and tell technical question. There will be a big thing about factor of 2. So bring your own factor of 2 and what argument there is for it, for and against. Be ready to fight. Is there one other question by young people? Because they are so good. The questions of the young people and the young people themselves. Yes. And ladies.
Sure, do I qualify as one young people? But the question was that when you talk about dark states, which you can sort of tune from being G1 to S0,
yeah.
There was some discussion about being a 2-photon emitter, which I didn't quite follow. Can you use this to create a 2-photon source?
So to have these dark states, you need to have 3 states.
Yes.
Actually. 2 of them, it's a combination of 2 stable states, and you have to have a bright one in the middle that you never populate, but you kind of off-resonantly couple through it between the 2 others. So this is what helps you making your single photon source more efficient when all you have is an atom and a cavity. If you only use 2 states, then your efficiency is going to be limited by a factor of kappa useful losses, my cavity transmission, divided by itself plus the atomic decay. And that atomic decay goes away when you can play with that dark state. So that was the message.
Okay,
so
still a single photon source, but
yeah,
more...
It's a single photon source in that case. But the message was just like when you go to conferences, you often hear people who only have 2-level emitters saying that you have to have a bad cavity limit to make a single photon source. It's not strictly true. If you have a 3-level emitter that you can play with, you can get around that limit.
Thanks.
Okay, then let's go for tea, coffee. We can keep on discussing, and then we'll come back in 10 minutes.
On m'a demandé un tuto.
The next speaker will be Ambarish Ghosh from IISc, the Indian Institute of Science here in Bangalore, apparently not so far away from here. He will be talking about bubbles in helium superfluids, so that sounds kind of cool. The floor is yours.
Thank you. Thank you so much. It's always a pleasure to visit the neighbors here, which we don't do often enough, but so thanks for the opportunity. I purposefully kept it a little bit away from the atomic vapor community. There seems to be some echo, right? Hello? Are you okay? Yeah? This is fine? All right. Okay, good. Good. Thank you. So I'm primarily at the Center for Nanoscience and Engineering and also an associate faculty in the Department of Physics. And this happened in the physics lab, which I hope some of you will come and see. The theme of this conference is quantum, and this is kind of an interesting quantum material in which it's nanoscale and it's soft. And the softness part is, again, has some correspondences to many of the systems that the community here looks at. But then there are these additional things in which we are talking about few body physics, and the superfluidity, in all honesty, does not quite come in. You can just take it to be bubbles in any liquid. And here bubbles means bubbles, really, right? A little cavity inside a liquid. That's what we are talking about. All right. So the outline is the following. I'm going to just describe what few electron bubble is. And then I'm going to tell you about an experimental technique that we use, which actually uses sound to explode bubbles. And then specifically, I want to tell you how these bubbles with 6 electrons are getting formed and how we are detecting them. Okay, so it's about getting light, quantum fluid, electrons, light scattering, all of them in one go. And the entire physics of something with a fixed number of interacting particles on some form of a spherical shape or a spherical system is related to a well-known Thomson problem. I'm not sure how many of you know. This is something that you can search in Wikipedia. If you have a spherical surface and then you put a certain number of interacting particles, what are the various ways they can rearrange themselves? And this is actually related to a wide variety of different scientific phenomena. So if you search with Thomson problem, you will hear a lot of literature last 100 years, 150 years of research that has gone into it. Ours is effectively the Thomson problem, but on a soft interface. Okay? Our surface, our sphere is not a perfect sphere. It can become a little bit ellipsoid, it can fluctuate, and that makes things quite difficult, quite different. So this was primarily Neha's work, but then subsequently Dilip, who is standing here, has actually extended it to much more interesting places. And just in the last slide, I'm going to tell you a little bit about some of the recent things that Dilip has done beyond 6 and 8, and we are all extremely excited about it. All right, so the experimental system is between electrons and helium atoms. Helium has a closed shell, so therefore any extra electron that you put inside a system of helium atoms will get repelled, and this repulsion is purely quantum mechanical in origin. You can imagine the helium atoms, which is shown in red here, to be almost very, very weakly polarizable. So you effectively can ignore all the long-range interactions, but only worry about a short-range Pauli-exclusion principle related interaction between this extra electron and the helium atoms. So the helium atoms just gets pushed away, and the electron basically sees a little cavity and sort of self-localizes itself. All right. So then this electron turns out to be of course it's not correct to put it as a solid sphere, but it indeed resides in some form of a quantum mechanical state. It's a textbook example of a particle inside a box. All right. So the particle here is electron, and the box is made by a bubble made of helium atoms. And then the shape and size of the bubble is effectively governed by two things. From the inside, the electron pushes out, which is related to the quantum pressure that the electron would exert. And from the outside, because the bubble surface is curved, surface tension would want to put it back in, right, to make it flat. And then if you have any extra pressure applies to the liquid, that also tries to push the electron back. So these are the two competing mechanisms over which this bubble is made stable. And when I say stable, it is indeed stable. the energetics of this electron bubble system is about 100 millieV compared to the electron and the helium atom. So it's a perfectly stable system. And in the temperatures that we are talking about, 4 Kelvin or lower, this is infinitely stable for all practical purposes. So this is what I called a single electron bubble, a bubble that has a single electron. The size of this bubble can be found out very, very easily. You can write down the total energy of the bubble as some surface energy, where sigma is the surface tension. If you apply any pressure to the liquid, you have to do some thermodynamic work, some PV type of an energy. If P is 0, then this goes away. And then you, of course, have the quantum mechanical energy for an electron particle in a box. This is a textbook problem. It goes as h squared by atom r squared, right? So there is a 1 over r squared term. There is an r squared term. So, of course, you can easily minimize it. And then the energy shows a minimum right at around 2 nanometers or so at a 0 pressure. So to summarize, what we have is a 2 nanometer bubble inside which there is a single electron. And, you know, there is no shielding, none of that. So this object behaves like a bubble of charge 1 electron. Right? So that's the basic experimental system. Now, of course, you can play around with it. You can imagine. So, you know, it does not need to be in the ground state. You can excite them. You can you have more than 1 electron? Can you have many electrons? These are some of the questions that people have addressed over the years. But I must tell you, a lot of understanding about superfluid helium came because of this particular object. Because they are a very well-defined defect state. They can be moved with electric fields. So just by looking at their motion, looking at their response to electric and magnetic fields, one is able to find out very meaningful information about superfluid helium-4. This will work both in helium-4 as well as helium-3 and many other cryogenic liquids. The only thing that you require is that the electron and the atoms have some form of a short-range repulsion. That's all. All right? This, in fact, also gets formed in certain hydrocarbons, petroleum. In fact, it can also happen. Okay? All right. So the question that we want to address is, can you have many electrons inside the bubble? And the first, I will ask the question, okay, just before asking this question, I want to take a step back and say that, okay, what happens if you forget even about a bubble, but just consider a surface? Let's imagine a surface of liquid helium, and then you have a vapor. What happens if you put electrons? Exactly by the same reason, the electrons would have difficulty going inside the liquid because helium atoms repel electrons. So the electrons, on the other hand, does have a little bit of a long-range interaction between the electron and the helium here. So as a result, it forms this beautiful bound state. So what you have is a layer of electrons that are floating on the liquid surface. So what you have is a charged interface. So if this is the liquid surface, the electrons are a couple of nanometers above the surface and forms this beautiful two-dimensional system. So now what you have are waves on this surface, and the waves of this surface can be governed by some form of determined by gravity, given by surface tension. And then, of course, if there is a charge and electric field due to these electrons, the dispersion relation of these waves get modified. So this is the standard physics of a charged interfacial wave. This is there in almost any liquid vapor interface. Now what happens is, and this is the interesting part, as you keep on charging, as you keep on putting more and more electrons, there is a negative term in this dispersion relation. Another way of saying this is that the frequency of these waves actually starts reducing, so it becomes softer and softer. So beyond a certain electric field, the frequency of certain modes can go to 0, and a 0 frequency in dispersion relation for the students here corresponds to some form of a hydrodynamic instability. So schematically, what it looks like is if you keep on increasing the electric field or the number of electrons more and more on the surface, at some point these waves cannot come back. They do not behave like nice waves anymore. The waves suddenly become unstable and results in the formation of large bubbles. Just to tell you that I am not just dreaming up this is actually a movie of this phenomena in which the liquid surface starts showing some form of an interface, the bubble breaks and the bubble comes, the surface breaks and the bubble comes out. And this bubble along with it takes about 1 million or so electrons with it. And you can do the numbers and figure out that's indeed the case, okay? This is a high-speed image of inside a cryostat, an experiment done at about 2.3 Kelvin or so, in which you charged it and you see that at some point, boom, it breaks and forms these bubbles, okay? Yeah, go ahead. So this, very good question, I should put that. This would be of the order of 75 to 100 microns. the size of the bubble. So we are talking about a couple of millimeters.
Superfluid.
This does not have to be superfluid. You can do the same. In fact, this particular movie is done in normal fluid. That's why 2.3 Kelvin. And you can also do it in helium-3. At least in our lab, helium-3 is not superfluid yet. We can only go up to 10 millikelvin. So it also works in normal fluids. In fact, the same will also work with liquid neon.
Thank you.
Okay. So there's been a wide variety of the work that has been done. One of our main things, and the lab sort of started with this, is that we were the first ones to actually trap these multi-electron bubbles, and the entire research program sort of got developed with that. So then the bubbles came out, and people only observed them, but we were the first ones to actually trap them, and we use Paul trap for that, so that all of you guys use all the time, right? All right. So what have I told you about? I've told you about these big bubbles containing a large number of electrons. The physics now is extremely simple. So this is for large Z, or large number of electrons, or what I would call it a many electron bubble. The energetics is same as the surface energy. There is still that volume energy. And now, because things are so large, you can ignore the quantum confinement energy. And the only energetics that really plays a very major role here is the Coulomb repulsion between the electrons. So now the whole system is still completely classical. You can actually now have a spherical system, which is a system of interacting electrons, and this is the so-called Thomson problem that I was telling you about. The electrons will naturally self-assemble into some form of a state that minimizes the energy, and depending on the temperature, the system can be in a liquid state or a solid state. The electron crystal can melt or not melt, and this is something that Sri Ganesh, who was here just a little bit ago, has a poster on, so please talk to him and give him some details, okay? So most of my talk is not about it. This is about much larger objects, which is where the quantum terms are negligible. The question that we want to address is what happens for small z. When the bubble sizes are, when the number of electrons is smaller, the bubble sizes will be smaller. The quantum corrections then start becoming more and more important. So this really is the crux of this presentation. Imagine instead of one electron that I told you about, you have 3 electrons. Now these 3 electrons are now going to push each other and get pushed by the other 2. And as the electron gets pushed, it also starts pushing the helium surface, because helium is a very soft material. I think that softness is really helping it out. So then the shape does not remain spherical anymore, but instead what you have is a slightly deformed 3-dimensional object. So what you are seeing here is some form of a calculation that tells you what is the lowest energy of this system, where you have the electrons interacting with each other through Coulombic interaction, and the liquid surface also pushes it due to the surface curvature. And then what you get as the final answer is a shape like this. So this, what I would call a 3EB, is this object stable? What that means is, if by chance this object gets formed and then you have slight perturbations in the system, would it remain there, or would it rather break into 3 single electron bubbles? That's the question, okay? So folks have done these calculations. It's basically looking at the dynamics of this, and the answer that turned out was this specific object will only be stable in this narrow pressure range between minus 0.78 and minus 0.9 bars. So in other words, you have to put some negative pressure on the liquid, or you have to put some tension in the liquid, and then the bubble will be stable against small fluctuations. So in other words, for all experimental cases, this is an unstable situation. So then folks went ahead and tried to do a few calculations on this, and then the answer turned out to be the following. The only objects that they could find were stable in positive pressures were the 12-electron bubble, in which what you are seeing here is the electron sort of forms a configuration like this, and the bubble shape sort of goes around. And then what you see, it's stable in the pressure range between plus 0.5 and minus 0.3. The 8-electron bubble can be in 2 states, in which there is one square and then another square, and then in a slightly different configuration in which the other square is slightly rotated. So both of these configurations are valid, and it also allows for a stable bubble shape, stable bubble in a positive pressure. 6EB is interesting, which means that It's stable up to minus 0.6 bars, but it's 0 bar is the critical limit, which means this is really a big question, is it stable or not? But this was the theoretical calculations, and I'm sort of taking the pictures from this particular paper, but this whole entire problem has been looked at by theorists over a very, very long period of time. This includes quantum pressure. So for everything out here, you've got to have the confinement, quantum confinement plugged in. What you might ask is, do you need to have exchange interactions also included here? The answer turns out to be exchange interactions are almost negligible.
Okay, but if you don't have the quantum pressure term, then these are not stable.
Then, well, if you do not have the quantum pressure term, then effectively you only worry about the Coulombic term, and then then it's an entirely classical system, and then you will not even be able to, well, A, the energetics will be incorrect because the quantum correction is very large, and B, I'm not sure if you ignore it what you will get. But in any case, I think compared to Coulombic term is the quantum term that dominates for this small set. So
when you say the quantum confinement, so what is the length scales you are considering?
Good. So we are talking about things of the order of, so this entire object, I really should put some scale bars here, of the order of 10 nanometers here. Okay, so this, yeah, absolutely. So the individual electron is always getting confined down to about 2 to 4 nanometers. So there the energetics is very large. So it's very strongly confined. And see, at the end, the Coulomb interactions are long range. So that really reduces all exchange effects, basically.
Because I saw that 106 micron at the left side.
That's right. I really should put it. Thank you, Shabtoshi. I'll correct it for my next talk. There is the... Thanks. Yeah, so the pressure range, this is where it is stable, okay? So just to summarize, you have this single electron bubble. A single electron is strongly quantum confinement, but there are no interactions in this system. Then you have this multi-electron bubble with a very large number of electrons. This is a classical system, basically. It has strong Coulomb interactions, though. But then somewhere out here is a few electron bubble, but there are strong quantum effects, strong Coulomb interactions, and it's soft, so it has this soft quantum interacting nanomaterial. Okay, that's what we want to talk about. So we want to study them. How to? This is all theory. Now, you can imagine the following. You can start with optical absorption, and people have done that. People have looked at the optical absorption of these things, but the optical cross-section is actually very small. So it happens in the infrared, and you need many bubbles. So the experiments that was done almost 50 years ago, we were talking about some billion bubbles in a small cross-section. Only then the signal was large enough. You can do electrical measurements, but it's a very, very difficult electrical measurement to do with single electron sensitivity. And if you look at the numbers, it's just an impossibly difficult experiment. Okay? So we had to come up with a way in which you would be able to detect some bubble-like species, which will also tell you how many electrons are there in the bubble. Okay? That's a hard experimental problem. And this entire technique of, and of course you can also see it directly, but that will not work for a 10 nanometer bubble. Okay, it's impossible to see it because helium by itself has a very, very low refractive index contrast compared to vapor, so light scattering will not work. Okay, so none of these things work. So we had to come up with a new technique, and this was part of my PhD technique, which started before me, but then I carried out long time back, using cavitation, using sound. And the idea is the following. Imagine you apply a sound, okay? Before applying the sound, let's first look at this equation. I already told you about this, right? So there is a surface term, there is a PV term, and then there is some other term due to the presence of electrons or something else, some hydrodynamics in the system, blah, blah. It doesn't matter. What matters is this particular term, the pressure term. You can have the pressure term to be positive or negative. Positive pressure means you apply some stress onto the liquid. Negative pressure means you try to pull on the liquid. Okay? Liquid can be both pulled and pushed. Depending on the pressure term, you would see, because there is an R-cube dependence, there seems to be a very critical pressure at which you would not be able to find a stable minimum. What does that mean? That means if you have this completely stable object in a liquid, and now you start pulling it, there seems to be a certain pulling amplitude or a certain pulling strength at which the bubble will not remain localized, the bubble will just grow. Of course, you cannot do it experimentally, like the way I have written. it always has to be some pressure oscillation, which can come, for example, from sound. So by applying sound and slowly increasing the sound amplitude, is there some certain amplitude of pressure at which the bubble ceases to be in a bubble state but just grows exponentially? So the experiment, the movie that you are seeing here is exactly that. What you have is a focused ultrasound. The sound is getting sort of converged in a certain point. If an electron bubble happens to be here, during the time when the pressure amplitude is lower than minus 1.89 bars, this few 2 nanometer bubble is going to explode and become a 100 micron bubble. So effectively, sound creates a hydrodynamic instability such that to make this entire object visible. So what you are seeing here is all liquid, it's just bubble, but somewhere inside there must be a single electron. Okay, so that was the key cavitation technique that was done at Brown over more than a decade. Okay, this movie was taken, but just the cavitation technique. The movie was taken from this paper, but the cavitation technique has a very large number of experimental details that I'm completely glossing over right now. But that's the key idea. Yeah. So I'll tell you what we did. So basically the idea is if you have a critical pressure like this, effectively below a certain pressure amplitude, the 2 nanometer bubble will become maybe 3 nanometer, and then it might become half nanometer. It will just oscillate. But once it goes beyond the critical pressure, right at this point, the bubble starts to grow to macroscopic sizes. And that's what you can detect experimentally. This is like a schematic way of looking at this instability. What did we do? Well, what is our technique? This particular critical pressure, if you look at this math, will get modified if this particular term, the quantum mechanical term, changes. So in other words, the critical pressure at which objects become unstable depends on the number of electrons. Okay? So this would be a way in which you would be able to detect this explosion event, and knowing at which critical pressure this happens, we will be able to find out the number of electrons. So we did this experiment. I'm going to completely grosso, not talk about the rest of the slides, but simply tell you just the basic experimental technique. Here we just used the planar transducer, so the sound just went and basically went from here to there. This is the, I think, the liquid surface. But then as we applied sound, you can start seeing these little black dots. So these little black dots are nothing but little explosion events that are happening when some bubble-like species is there and some sound is there, and together they explode.
When the bubble expands, does the electron number stay same?
It should, because you can imagine the whole thing is inside. There are some number of electrons. And then the liquid surface is going. So the electrons will also start getting repelled and go outward. There is no reason for the electrons to come inside. Okay. Crux of the experiment, and this data, there is a way of looking at it in detail. If you look at the number of such events, depending on the transducer voltage that we apply, which in other words is related to the pressure that we are applying here, we observe effectively little kinks. And these kinks, when you look at it very closely, these voltages correspond to some new species that comes in. This is just one representative data. Okay? What we see, if you look at it very closely, is that this corresponds to one certain species of bubbles. So the single electron bubbles will be way somewhere out there, okay, which we are not even trying to detect here. But somewhere out here, we start seeing a little bit of a kink here and then a larger kink here. This corresponds, and there are only 2 such kinks that we could detect. If you look at the numbers, because we know at which voltage this is happening, so we know at which pressure amplitude they are exploding, that turns out to be exactly at minus 0.59 bars and 0.38 bars, which matches exactly with the theory that people have predicted completely independently. There is absolutely no fudge parameter, no calibration, nothing out here. Even the numbers match exactly. We were very unhappy that we could only detect the 6 and the 8 electrons, but now Dilip has also managed to see 12 electrons because he now has an improved technique of these objects. So we match exactly what were the ones predicted. The important point is, and this is the crucial point, this effectively is like a spectroscopy technique, right? At which point these kinks come, right? And it gives the kings at exactly the 3 points that the theorists had predicted to be stable. So that was very, very, it's kind of satisfying to see when these things match correctly. I will completely go and perhaps not even talk about how they are getting formed, but because this is also important, but just very briefly, what we believe is happening is that these big multi-electron bubbles get formed, they break further, and only the stable ones remain. And what are the ones that are stable are the ones that are 6 or 8. This is one of the ways in which these objects are getting formed, okay? I will completely go away from this particular thing, this ultrasound and all of that, but simply tell you one mechanism which is kind of interesting, in which sound by itself can also form this 8 electron bubbles. And just schematically, the way it happens is the following. You have a charged interface, and this is the standard math of parametric coupling. I'm not going to go into this, but the key point is you can imagine this is a liquid surface on which the electrons are floating. And then when you apply sound, this surface starts to oscillate at a certain frequency, which will be given by your sound wavelength, which is some omega s. But then this particular system, which is a little dimple that gets formed on the surface, has its own characteristics frequency. There can be phenomena in which the sound frequency and the intrinsic wave frequency would be a multiple of each other, in which there will be a parametric instability of the surface. And this is one of the ways in which a system like this can become unstable and starts creating this submicron scale bubbles. Okay? I'll not go into this detail, but all of these things are present in the paper. Okay? So let's not get into all this. So the key conclusion is there are 6 and 8 bubbles that were observed. Now we have 12, and we also observe certain species, which is around z equal to 50, that are present only up to a certain positive pressure. This will be, hopefully, I'll be able to talk about it in some time. But right now, as far as I know, this is probably one of the first demonstrations / confirmations of this Thomson problem in a soft material. So indeed, this is something that we will be trying to do, is to trap these objects and then try to modify the pressure to see if we can tune their electron interactions. So with that, I would like to thank you for your attention.
Thank you very much for this really refreshing talk. Questions? Yes, please.
Yes. Hello. Yeah. So I had the question: how do you detect the defects in the which you said that the species, the kinks in the entire graph? How do you ensure that they are the exact places? Because
absolutely. So we know the voltages at which the kinks happen, and we know what voltage corresponds to what pressure oscillation. So that's a separate calibration that we do. And that's done completely independently. So the very simple way of doing it is, so for example, when you apply a voltage, you would see some pressure oscillation, but then we can measure it by simply looking at which point, for example, the surface starts giving mist. And there are standard hydrodynamics theories for it. So this is the most standard way in which ultrasonic transducers are calibrated.
just one thing, the error bar is also very large there.
Absolutely. So this is just a representative data for the 8 electrons, but there are other things all in the same paper where the statistics is orders of magnitude higher. Right. It's all there in the paper. Yeah.
Thank you.
The 6 is much larger statistics, the 8 were small, which is why we looked at 8 using other techniques as well, where the statistics become much larger. So I'm not going into those details yet.
Okay.
So.
Thank you.
I'm giving priority to young people. I'm not.
At some point, you showed that when you have this interface between the vapor and the helium, and you increase your perturbation, you have this minimum in the dispersion relation at a finite wave vector.
Mm-hmm.
I guess if you this time have a superfluid helium, you can relate this to a super solid.
Sorry, once again. So
Can you basically interpret your surface?
So I suppose you are asking if the interfacial properties can be related to superfluid-like behavior.
Yes, with a
of the
periodic
surface.
special structure, which they call
Yeah.
supersolid.
So just to, okay, so I'll go first to the solid part. So people have tried to do these experiments where you have a liquid-solid interface in which you put electrons and look at charged interfaces, unlike us where we do liquid-vapor interfaces. The interesting thing is you cannot have a free electron there, but instead you will have an electron bubble there. So people have made a solid liquid interface, actually solid below, liquid above, floating, and the electron bubble will go and decorate just like these guys. And you would see very, very similar things. The instability there is reversed because it does not become unstable like in that manner anymore. So it becomes unstable in a separate, there is a separate pathway for that instability. I have to go into a little bit more detail, but it's not free electrons anymore, it's bubbles. That's the main point.
Okay. Thank you. Can I ask just something quick more? Maybe it's a super dumb question, but have you, when you look about, you're interested in the stability of bubbles, and you said you didn't manage to see 12 electron bubbles yet?
We have. So he has seen it now.
Okay, cool.
We have, yeah. It's just a matter of numbers. The number of 12s were even smaller than the 8. So now we have statistics where you can see 3 kinks very, very clearly with 12, 8, 6. So we have to come up with a new sound focusing technique for that.
But I was thinking, can you imagine that the 12 electron bubbles decay in 2, 6 electron bubbles, and this is why you cannot see it? Maybe this is super likely to happen.
So theories suggest that they should be stable. The energy gaps are actually significantly larger than the temperature. So if they are stable, they should be stable forever.
So how you end up this decorate vortices from electronics bubbles? So
Yeah, so thanks for noticing that. Yeah, so I didn't talk about that. So just in superfluid helium, you can have these topological defects which are in the forms of vortices, vortex lines, like cyclones. The only interesting thing is the circulation, which is effectively the integral of velocity along a closed contour, has to be quantized. So just for everybody else, so these vortex lines are quantized in superfluid helium. And just like any cyclone, it traps things, so the bubbles can go and get trapped there. So effectively, all the 6 electron bubbles, single electron bubbles, they all get trapped. And some of the movies that we showed there, you would see that a certain lines were getting decorated and we were exploding them. This is very common in superfluid helium. It is the difference of critical pressure for a bubble on a vortex versus off a vortex is very small. So you would still be, your spectroscopy would still work.
Pressure is enough to create vortices in that. There is no external angular flow.
Oh, this vortex is happening because we are generating a large amount of heat into the system. So that generates a large amount of normal fluid flow. As a return, the superfluid has to go backward. So this counterflow is what creates the vorticity in the system. In fact, the entire system should be in a semi-quantum turbulent state in many of our experiments.
Okay, nice, thank you. The another one is like you said there is big bubble which is fermented or break down into the small bubbles.
Yes.
So how do you, quantify? There would be some critical value of some quantity. After that, it would end up into some small number of bubbles. What is that quantity?
If you believe the standard theory, there should not be any bubble stable with pure classical interactions because of certain mode instabilities. So that 6, 8, and 12 are stable is the most surprising part. Everything else should be actually unstable. However, this instability is based on certain very classical arguments. Any small quantum correction can make it fully stable or make it more unstable. And we believe all of that is happening when Z is small. So you're basically on a knife edge, and a small quantum correction can take you either way. And that's the sort of physics we are looking at out here.
Okay, this instability you are talking about, you look it from this density perspective, like when it break down into the small vortices, or you were talking about some frequency also?
So this is a quadrupolar mode instability. Yeah. So in other words, if you look at a certain bubble, it can have a breathing mode, right? Yes, that's your L equal to 0.
Yeah, right.
But then you can have bubble shapes and shape changes in which it looks like a peanut.
Yes. Yes.
Now, this is like last 200 years, starting from Lord Rayleigh, even critically charged droplets, critically charged bubbles, all of them have this L equal to 2 or quadrupolar mode that's unstable. So that instability is what...
From the excitation.
correct. So that can go either way. Basically, that omega 2 is 0.
Thank you.
Okay, one last question, please, and then we can move
The one
on.
guy at the end, right?
This is kind of quick. Okay, when you were talking about the eight electron bubble, you said that there were 2 stable configurations. I would expect there's a minimum energy configuration, right? So you would typically go into one of these 2. So, I mean, how is it that 2 are manifesting?
So effectively, I don't know the energetic part. So the way these things were done, where you start with the electron configurations, then you try to find a shape, a stable shape. And when I say stable, it just means that if you do minor shape and size fluctuations, whether the electron will, whether the bubble will break into smaller bubbles or not. That's the way the stability calculations were done. What you are asking is, how did it in the first place go into this configuration versus this configuration? Not clear, Sadiq, not clear. We don't know the answer to that.
Because we intend to do that anyway, so we'll figure it out.
I think one of the ways of doing it in here is to start from a higher temperature so that the system is in a liquid state and quench it into one of the 2 possible solids. Easy to say, but...
All right, thank you very much.
Thank you.
Let's try to move on to the next speaker.
Thank you so much. আমি একটু বেরিয়ে যেতে হবে, খুব বাজে অবস্থা আমার। No, we are fully.
Okay, excellent. So the next speaker is Subro Bhattacharjee from the International Center for Theoretical Studies, ICTS. Please, introduce yourself a little bit, and I'll give you a sign 5 minutes before the end.
So
of
it's
your
at 20 minutes you would give me a... Okay, thanks. Yeah. Okay, so let me start by thanking the organizers for having me and also allowing me to speak on the first day because of date constraints. Thanks. So what I'll be telling you about is some of the things that, we made some progress in a rather old problem, which I'll try to explain to you, and it would be sort of different flavor than the previous talk that we heard. So I'll start with some of the basic introductory things, but will quickly try to explain you the problem that we have and the progress, and then I'll discuss some of the technical details. Okay, so the people who are collaborators of this work, which is going to appear soon in PRB, is Sergei Moroz from Karlsruhe University and Angus Chobe, who was a graduate student at ICTS. So let me start with like a lightning introduction. So anything that we know, all electronic phases of matter lies in one of the 4 quadrants, starting with simple things like symmetric broken phases, ferromagnets and superfluids, to more exotic things like fractional quantum Hall effect, topological insulators, and metals and semimetals of various kinds. Now, the point is, the way of understanding all these things is trying to ask how does the high energy description in terms of electrons and ions, the system quenches the thermal entropy as you cool the system, and in the process various kinds of low energy descriptions or infrared or IR descriptions appear. And there are 2 major ways that we know about. One is more classical, where the system breaks various kinds of symmetries, and that leads to almost product states, and these are very well understood phases, the symmetry broken phases. In fact, all the technology that we use are based on these kind of the phases that are described by various kinds of order parameters. But what we would like to understand more are these quantum ways of reducing the thermal entropy, where you typically take this high energy degrees of freedom and choose a superposed many body state, which leads to a lot of quantum entanglement, and this quantum entanglement is underlies all the properties that we know about. Okay, so one of the characteristic features of how this goes about for this quantum phases is that we start with some degrees of freedom at high energies, ions and electrons, which typically have tensor product Hilbert space. But once we go to low energies, this tensor product structure is lost, and because of this, all the other things that we know about how the symmetries act on the system and how the degrees of freedom interact with each other all gets very complicated and very different from things like ferromagnets, etc. So one place where this occurs again and again, and this has various kinds of realizations, are what are called dimer models. The earliest version where these were noticed is frustrated antiferromagnets, starting with, say, 2 spin halves. If you take 2 spin halves and think about this kind of interactions, the ground state is a singlet, and so when you take a frustrated antiferromagnet where spin-spin interactions compete, these kind of singlets may survive as the low energy degrees of freedom, and this gives rise to what are called dimer models. The problem with dimer models is that if you think about, say, forming these kind of singlet coverings where each this ellipse denote that 2 spins which are part of the same ellipse form this dimer, forms a dimer. Each spin only is a part of one dimer, and so if you count the number of dimer coverings, it does not go as the number of spins, but a lesser number, and in other words, this arises from this constraint that the spin is at most a part of one dimer, and so the dimer Hilbert space is not a tensor product Hilbert space, because as you go around throughout the lattice, you have to, you cannot say that I can decide on the dimer at every site or every bond independently, and hence there is no tensor product structure. You have to always obey the constraint that if I think about the dimer number, the dimer absent being 0 and dimer present being 1, then as I count the dimer number at every site, I must get 1, and there is no unique way of getting 1, but I have to make sure that this constraint is obeyed at every site on the lattice. So this gives this thing that the low energy degrees of freedom, if they are dimers arising from antiferromagnet or Rydberg atoms or bosons with repulsive interactions, the low energy Hilbert space have this weird thing that I cannot specify the state of each dimer separately, and I have to basically obey a constraint like this. Okay, so then these degrees of freedom, which in this case are dimers, as I said, that they do not have a tensor product Hilbert space, and this immediately affects how symmetries act on these degrees of freedom at low energy, and more mathematically they do not obey the linear representations that we are familiar with in case of magnets and superfluids that we heard, but have these projective representations. And then one can think about interactions between the dimers. Typically one can write down a Hamiltonian in the same spirit as particles. There is a kinetic energy term and the potential energy term, which now obeys this constraint that there is one dimer per site, and none of the dynamics must break this constraint. Okay, so let me tell you about the potential energy term. So I have dimers like this, and the potential energy basically either depending upon the sign, either favors these kind of the configurations or penalizes this kind of configuration. There is an energy cost to this. On the other hand, the kinetic energy basically leads to flipping of these dimers on the flippable plaquettes, and this is essentially the low energy dynamics of these dimer models. Okay. So people studied this for a very long time, starting with late 80s, and what they realized is that these kind of Hamiltonians going under the name of Roxer and Kibelson realizes only solid phases of dimers, where dimers are arranged either in the staggered way or in the columnar way, except for a point, fine-tuned point, where both these coupling constants are equal, and that represents a long-range entangled phase as a critical point, often called the resonating valence bond liquid. Now, the problem is that these models were studied in context of cuprettes, the cuprette superconductivity, and realizing such a resonating valence bond liquid was central to some of the programs initiated by various people as to understand the superconductors as doped versions of this RBB. But since these RBBs were rather fine-tuned and was never realized as a phase, this program essentially collapsed because there was no RBB to the generic RBB phase to dope, and there were various efforts throughout the last 20 or 30 years trying to open up an RBB phase on a square lattice in these kind of dimer models. But it looked like that this is a hopeless case. All you get are different kinds of solids. Okay, so what I'll tell you is that we made sort of some progress in this direction. What we managed to do is using a particular qubit regularization of the dimer models, we opened up a whole phase diagram where there is a Z2 quantum spin liquid, which opens up along with this solid phases of dimers. And central to it, rather technical, is a multi-critical Yuan spin liquid with a dynamic critical exponent of Z equal to 2, which seems to be the central to this phase diagram that people may have missed earlier. Okay, so this is what I want to tell you about in the rest of whatever time is left and how this works out. So the qubit regularization of the dimer Hilbert space works in two steps. The first one is trying to map the dimer to some dual bond Ising spins, and then implementing the single dimer constraint through energetic penalty instead of projections that people typically have done to obtain generalized Ising dimer models. Okay, so let me explain these to you in steps. So the first thing is that this red wiggly bonds are the positions of dimers, and one can think about drawing the dual lattice, which is this black lattice, and every time you have a dimer, you can associate an Ising variable on the dual lattice such that this Ising variable is plus minus 1, appropriately denoting the position of the dimer. And then one can translate the constraint on every site of the dimer to a placate constraint on the Ising variables on the dual lattice, and this is just rewriting of the degrees of freedom essentially, and then the kinetic term basically becomes the flipping of the Ising variables on a site, whereas the potential term becomes some Ising interactions of these dual Ising spins. Yeah.
Yes, I'm a bit lost. Can you come back
Yeah.
one slide? Yes. So here, which is what is the initial lattice?
So the initial lattice is in red. As you can see that there is one dimer per site. Okay. so let's take this bond, okay? So this Nij is +1 on this bond. So this Zij is -1. So that's the dual Zij, which crosses this bond, is -1. That's how this mapping works out. Okay? So to every bond on the direct lattice, there is a unique bond on the dual lattice. Okay? In other words, every red bond uniquely crosses a black bond. Okay?
What's the purpose of going from the dimer to the dual bond?
Yeah, you'd say, just give me like a few minutes. Okay? Yeah.
Just a simple question.
Yeah.
So here I'm trying to understand you are just using them as isolated dimers, or you also have some inter-dimer interactions. So how will be the Hamiltonian looking like?
Yeah. So as I said, that this is the Hamiltonian. Okay? So there is a dimer-dimer interaction and a kinetic energy term. Okay? Yeah. Okay. So more questions? So one can rewrite all these things. These are the ways of just rewriting these degrees of freedom in terms of these Ising spins. And then the point is that now I have a constraint on each plaquette, and I can implement this in energetic fashion that includes two terms. The first term is basically trying to have this kappa term, which basically wants to have odd number of spins in a plaquette, odd number of Ising spins in a plaquette to be -1, and then there is a term which picks out the dimer, the manifold. So I can discuss the details. Essentially, the point is that through adding this energetic penalty, one can basically obtain the dimer manifold in the large kappa and the J limit. This is a one-to-one mapping of some variables, which I can discuss after the talk. So once I have these two things, there is my original dimer model with the kinetic term and the potential term, and then I have this energetic penalty, and this consists of the generalized dimer model, or which provides a qubit regularization of the original dimer model that I started out with, but now it lives on, is described in terms of Ising spins sitting on the bonds of this dual black lattice. And I would like to try and understand the nature of the phases in this case as a function of the coupling constants of the dimer model. Okay? So let's try to understand the Z2 liquid limit. So I take this Hamiltonian and just think about the large kinetic energy of this generalized dimer model. And what one can show is that one realizes an exactly solvable model, which is known as the Toricode the spin liquid. It's a Z2 spin liquid where the ground state is described in terms of fluxes of the Z variables at every plaquette, and these absence of Ising charges on every site, and the ground state actually is a superposition. So to think about the ground state, the ground state is actually a superposition of all kinds of closed loops of down spins in a background of upspin, and this the humongously the superposed ground state actually has a entanglement entropy of the area law minus log 2, and this log 2 is the topological contribution, and it comes from the fact that if I think about closed loops in a bipartition, the loops either cross the bipartition or do not cross the bipartition, but if they cross, the number of crossings is even, and that parity shows up as this log 2, and this is the and you cannot get rid of this log 2 because it's an even number irrespective of the number of crossings. So this topological entanglement basically prevents this ground state to be continuously deformed to a product state, and that's the ground state in the large gamma limit. But once you decrease gamma, what you see is that this entanglement undergoes the decreases, and in fact, if you calculate the correlation length associated, the largest correlation length of the system, it shows this peak and it indicates a phase transition. So what happens is that as you decrease gamma, you go from a quantum spin liquid at large gamma to a different phase at small gamma, and this is how the phase diagram works out in numerical calculations starting from the large gamma. So this is what the other two phases are. What happens at small gamma and large omega, you realize this crystal phases, the staggered crystal and the columnar or plaquette crystals, which are basically the old remnants of the Roxer-Kivelson model. So one can try to ask that how should one think about the phase transitions, particularly because the Z2 liquid is long-range entangled, so we don't have a long Landau theory based on order parameters. Anything that we write in terms of order parameters is going to miss the topological order, and to get the correct description, one needs to start from the anionic excitations of the Z2 spin liquid. How am I doing with time? Okay, good. So the Z2 spin liquid, whose ground state is the superposition of loops, has two excitations which are like electric and magnetic charges, but Ising electric and magnetic charges. What one can do is one can think about changing the product of the Z's around a plaquette from -1 to +1, and that describes what is called a Z2 Ising, the Z2 magnetic charge. One can do the same thing for the product of these X's around the sites from +1 to -1, and they describe a Z2 electric charge. The funny thing about this is that if I take one of these charges around the other, I gain a pi flux, which is this is sort of the Aharonov-Bohm phase of the electric and magnetic charges, the Ising versions, and such things. In other words, these electric and magnetic charges are basically mutual semyon. They always see each other as pi flux. But note that these are fractionalized excitations in the sense that if you flip a spin, you necessarily create two electric or two magnetic charges, and they are not order parameters of the magnetic of the crystals, and the low energy theory must be written in terms of these fractionalized degrees of freedom rather than the order parameters. Okay, so yeah, so this is the point that if you flip a spin, you create two electric charges, similarly for the magnetic charges. So one can try to ask what are the soft the electric modes, and the analysis of this theory gives us that there are two soft electric modes which are protected by the emergent symmetries of this problem, and one can go ahead and try to write down the field theory in terms of these soft modes, which describes the phase transitions. So the phase transition is now described in terms of the condensation of the soft modes, but the soft modes are not the order parameters, but the order parameter is some combination of the soft modes, which is why the phase transition is not of a Landau type. Okay, so one can do this analysis and write down the low energy field theory. The low energy field theory is in terms of these soft E and M charges, and the symmetry acts in a projective fashion on them, and because because of this, they couple to a mutual, they couple to a Yuan gauge field, and one can sort of write down the involved field theory to describe the phase transitions. So again, without, one can write down a sort of a slide full of low energy field theory. Essentially what one gets is that the field theory contains two coupling constants. These are the coupling constants related to the microscopic model. This coupling constant is related to the mass of the electric charge, charge, whereas this coupling constant is related to the kinetic energy of these electric charges, and one can try to do a normalization group calculation to track the flow and find out the various phases as I showed you before. Okay, so one can try to check this with actual numerical calculations, DMRG calculations done on cylinders, and calculate various signatures of these phases, starting with the solid phases and the liquid phases, which are now characterized by this the topological entanglement entropy. Yeah, done. So what we found is that central to this understanding of various interesting phases and phase transition is what we call a multi-critical Yuan spin liquid, where the dynamic critical exponent is z equal to 2, and one can try to understand various phases as various kinds of instability of this Yuan spin liquid, starting with the solid phases being given by the monopole confinement phases, whereas the Z2 spin liquid is a charge to Higgs phase, in the sense that this Yuan spin liquid seems to be the parent phase of all these different phases that one can obtain, and then try to understand the fate of this Yuan spin liquid. One can do various kinds of calculations, starting with the field theory that I show to basically sketch out this entire phase diagram and compare it with numerics. Okay, so let me on that note end with a summary. So what I said is a particular qubit regularization of the dimer model, and which allows us to open up the Z2 spin liquid phase as realized in a Tori code, and it sort of overcomes this question of Yuan confinement, which has plagued the field for like about 20 years or so, and gives us this a handle to open up this short-range resonating valence bond liquid phase. The central point seems to be this particular multi-critical Yuan spin liquid, and one can try to understand various phases, starting with this multi-critical Yuan spin liquid. So thank you for your attention.
Thank you very much. Questions? Yes, please.
Can you kindly repeat how the Z2 magnetic charge and electric charge are calculated in the Ising model?
Yeah, so let's see. Yeah, so let's try to take this limit, okay? So these two terms actually commute with each other. So to obtain the ground state, you can basically minimize these two terms independently, and what you do is for kappa to be positive and gamma to be positive, you want to choose this product at every placate to be -1, and product of every x variable, which is the conjugate to the z variable at every site, to be +1. Okay? So then the excitations are basically flipping these things. So at ground state, this was the product of z is +1 and product of x -1 and product of x is +1. So to create excitations, either you flip this or you flip this. Okay? So these are the two things. One is on the site, which is this, and the other. So now what you do is you try to think about taking one around the other, and that you can take this by flipping a bunch of spins, and irrespective of the path, you would find that your wave function winds by pi. Okay?
Thank you.
Any other questions? Young and not so young.
Yeah, so I have a very general question. So when you're talking about liquid, you must be like taking into account infinite number of sites, right? Like in the thermodynamic limit.
Yeah.
So can you like give an idea, like if we are starting from finite number of lattices and then keep on increasing the sites, and then can you certify like what is the some liquid like parameter that we can quantify, and that parameter will tell you that it's a liquid now. So as a dependence of your number of sites. So is there anything what you can say like this transition from finite to infinite, and then you can tell it as a spin liquid?
Yeah, so you can take this particular system, okay, and calculate something like spin-spin correlation function, which would be like density-density correlations in a liquid, okay? So it's completely featureless. So in fact, all few-point correlators are exponentially decaying in this system, okay? Yet, you cannot write down a product wave function for this system. So it is, as far as the correlation functions are concerned, it's completely trivial, it's featureless, okay? Whereas as far as the entanglement is concerned, it's non-trivial, so it's not a, so the correlation functions would tell you that it's like a classical liquid or a gas, basically completely featureless, but the entanglement tells you that it is a quantum object, a quantum many-body object.
So this is multipartite entanglement.
This is bipartite. You don't have to do you don't have to go to multipartite and all those things. So this is just bipartite.
Anybody else?
In your phase diagram,
Yeah.
the last one that you showed us, the key phase diagram, I don't think I was able to get what are the meaning of R and theta. And can you try to give me some intuition on what is R, what is theta?
Yeah. So let's go back to this theory. So you see that the Dymo model that I started from had two terms. One was a kinetic term, which basically led to these kind of flips, local dimer dynamics. And then there is a potential energy, which basically gives an energy cost favoring certain dimer configurations. Okay? So, for example, if you think about the red dimer, if this term is negative, it favors such parallel configurations. If it is positive, it penalizes such configurations. So it's very similar to particle, that there is a kinetic term which basically moves the particle around, and then there is a potential term which favors or disfavors certain configurations. So this is what the this is what the content of these kind of Hamiltonian is. So wherever you see gamma, you must remember that this came from the dimer kinetic energy, and this omega is related to the dimer potential energy. So when you do this coarse graining, in terms of the low energy degrees of freedom, you see that there are exactly two variables, okay? The first one is this difference of the kinetic and the potential energy, okay? So this controls how the how the low energy dynamics evolves, okay? So this is the gradient term. So this is the gamma term, and this J is now the cost of having a dimer, okay? So that's like having the mass of this system. So these are the effective low energy handles. So it's not a chemical potential, it's more like a mass, okay? So, okay, so those are the two axes, okay? The combination of these two turns out to be the right low energy degrees handles that we have.
Okay, we are running very late, so I guess we can thank the speaker and then move on to the next one.